我要去食早餐。 Welcome to the session on lattices and codes. The first talk is about rigorous foundations for dual attacks in coding theory, and it will be given by Charles Meyer Hilfiger.
Hello. Okay, good. Thank you. So I'm going to present you a joint work with Jean-Pierre Tillich about dual attacks and their analysis. So dual attacks solves the decoding problem in code and lattices, and this problem is at the heart of security of all code and lattices-based cryptographic primitives. For example, dual attack would impact Kyber parameter, which is a NIST standard. The problem now is that independence assumptions are made to analyze the complexity. And it turns out that they are not valid. In code, for example, Carrier and al. showed noticed experimental differences between what we should obtain under this independence assumption and what we obtain in real life. And in lattices, Duca and Poole showed that these independence assumptions just could not hold in certain regime. And this seriously questioned dual attacks. So the question really is now, does dual attack really work? And so the contribution of our paper is to show that dual attack in coding theory work. And to do that, we give rigorous foundation for analyzing them without using any independence assumption whatsoever. So first of all, I'm going to talk about dual attack and their analysis. So I said to you that dual attack solves the decoding problem. So what is the decoding problem? It's just that I will give you a binary linear code, which is just a linear subspace of f2 to the n. And what I give you also a noisy code word of this code. So I give you a y here, which is equal to a code word plus an error vector, which will be of small Hamming weight. And I ask you to return me this error vector. So the main ingredients for dual attacks to solve this problem will be to use the dual of the code, which is just the elements of the ambient space, which are orthogonal to all of the code word of C. So the thing is, when I say orthogonal, it's for the usual inner product in f2 to the n. And here the element of the dual code, H, will be called parity checks. So the main idea of dual attacks is just to notice that if I take a parity check which is of small Hamming weight, then I can compute y dot product h. Y is my noisy vector. And this is equal, by definition of y, to c dot product h plus e dot product h. And so, no. Yeah, I'll let you maybe. Okay, thank you. So what did I did wrong? This? Okay, no, good. Okay. So, so what you have, it's that here, because C is a code word and H is a dual code word, this term cancels out and you only have left E dot product H. And because E is an error vector of small Hamming weight and H is of a parity check of small Hamming weight, this dot product will be biased towards 0. So it will be equal to 0 more often than it is equal to 1. And so the whole idea behind this is you can make use of that, for example, of that principle to make a distinguisher, for example. So let's put aside the decoding problem for now, and we can build, using this, a distinguisher between a random y and a y which is a noisy code word. And what you will do is actually you will compute the bias of this quantity, and you will say, okay, if the bias is high enough, this is mostly with high probability a noisy code word. So more formally, what I do is I compute all the parity checks of yw, and then I will compute this bias function, bias of y, and essentially it's a sum over the parity checks of yw of some terms that is between either -1 or 1. And I normalize this sum so that everything lies between -1 and 1. And so, for example, you see here that here y dot product h, if y is a noisy code word, this will be equal to 0 often. And so this will be equal to 1 often. And so this term will be big. So the sum will be big and will be close to 1. So you make a decision. If the bias is big enough, you decide that y is noisy code word. The thing is, how big is big? So when you have a noisy code word, in fact, you have a theorem from Carrier and al. That states that the bias related to y is in fact just a function of w, the weight of the parity checks you computed, and the weight of the error. Okay? And so here, you can see that essentially this function, the bias, decreases exponentially fast in the weight of the error. Okay. So now I'm ready to give the most recent dual attack, which was introduced by Carrier and al. The idea here is really to solve the decoding problem, so to recover part of the error at least. So what we do is we split the support in two complementary parts, completely arbitrary, P and N, and we will try to recover the error on the part P. And what splitting the support in two parts, what it really does is that it actually enables you to have quantity that will be much more biased towards zero than the previous quantities. So for what we do, in fact, we compute parity checks of weight W, but are W small on just the part N. And we do as before, we compute y dot product H. This is equal to E dot product H as before. And now we split this dot product between the part on P and the part on N. Okay? And now by reordering this equation here, you see that y dot product H plus EP dot product HP is equal to this quantity here. And because E on N is an error vector actually, so it's of small Hamming weight, and Hn is constructed of small Hamming weight N here, this quantity will be biased towards zero. And the thing to notice, of course, is that because the support is smaller and because we will be able to take W much smaller than previously, this is very, very much biased towards zero. So it's a good thing for us. And so what is our algorithm? Basically, is that we will make an exhaustive search. We will compute for every x the bias of this quantity, and we will just return the x such that this quantity is the most biased towards zero. And we will hope that this maximum is given by EP. So more formally, what we do is, as before, we compute the set of all parity checks of weight W on N this time, and we compute a bias function for every x. So this is, as before, a sum, and of -1 to the power of y dot product H plus x dot product HP. And you notice, of course, as before, that if x is equal to EP, this will be equal to 0 often, and so this whole sum will be big and will be close to 1. So you will return x such that the maximum is given by, so the maximum, so x such that the bias is maximum. So now the question is, okay, how do you analyze this kind of dual attack? You just have to study the probability that the bias related to EP is superior to the bias related to all of the other x's. So Carrier and al. Gave a precise estimate of the bias related to EP. They showed that under certain conditions, it could be expressed as a function of W, the weight of the parity checks, and the weight of the error term. Okay, so this is good, and this is well approximated. And now, to study the bias of all the other x's, it is now that we need to make independence assumption, because it's not so clear when x is not equal to EP what this bias is. And essentially, we make independence assumption, and this will allow us to say that the bias related to x is in fact a centered normal with a variance that we can compute. So this is in fact very, very convenient for us, because then we can study this probability quite easily. So okay, so we have this independence assumption that gives us this model. So I sum this in a plot. Here in green, you have under the independence assumption the supposed distribution of the bias of x. Okay, so all the x that are different than EP. For example, here you see that you don't expect any x's different than EP to have a bias which will be superior to 0.05. Yeah. So for example, if you choose your parameters so that the bias related to EP is superior to the threshold, for sure you will know that, okay, with good probability, the maximum will be given by EP. So everything is good. The problem now is that you can run experiments, and so this is an extremely pathological case. So you have to, but the thing is, you see that experimentally, when you plot the distribution of the bias, for some parameters, it's not at all, it does not follow the green curve here. And in fact, what the problem is that the bias related to EP will be completely lost among many other x's, so you won't be able to recover it. So the first goal of our paper was in fact to understand this red experimental curve, to be able to make to understand it, to be able to make an analysis after that. Okay. So so the contribution is, one of the contribution is to give a distribution of the bias that will match the experimental curve. So what we do is, in fact, first we give a dual expression for the bias related to X. So I recall to you that X was defined as a sum over some parity checks. And when I say here we give a dual expression for X, it means that we will express it as a sum over code words. And essentially, we can show that this bias here is a sum over the product of two terms, ni in this term here. And essentially, this term here to the right will be, you recognize it as before, it will be decreasing exponentially fast in I. And ni is just the number of words in a certain code, which are a distance I of my error vector en. And this certain code, Cx here, is just the code which are such that it's just the code word of C, which are such that C on P is equal to X plus EP, and we are just only considering the distance and the n part. So actually, yeah. And so the thing is now you have there's two terms that will be competing because ni, when I increases, increases exponentially fast, and this will be decreasing exponentially fast, this term on the right. And the problem now is that, in fact, you know, I said we want to study the distribution of the bias. The thing is, the only random term here is ni. And the problem is we don't know much things about this distribution. We only know the expected value and the variance and some other things, but okay, so we don't know a lot of things. So to model the distribution for the bias, we need to give a model for this ni. And it's what we did. We said that essentially the ni were Poisson variable with good expected value, and the expected value, we can compute it. Okay, and so of course this model doesn't come from nowhere. It was very rational. And now what we do is with this model, we are able to predict perfectly the distribution of the bias, which is the distribution of the bias. So you see here that the red curve is this curve here, and the blue curves represent the bias when we replace the ni by the Poisson model, as I said. And so it matched perfectly with the experimental model. So now we have all the tools to, in fact, so now that we have a model, we can study the probability that, we can study the distribution of the bias and study the probability that EP gives the maximum bias. So, so this model can be used to analyze dual attacks. And in fact, we showed in our article that the most recent dual attack introduced by Carrier and al. Just need a little algorithmic tweak to be able to achieve the originally claimed complexities. And so what does this really shows is that dual attack in coding theory work. And in fact, lastly, you saw, so the whole point of the article, not the whole point, but key point of the article was to use this duality formula to be able to give another model for the bias. And this duality formula could, in fact, be also used to analyze the dual attack in lattices. Thank you very much.
Thank you. Any? Hi.
So does it change the security levels that we need for lattice-based crypto systems?
In fact, I don't think when this attack, the Carrier and al. Attack, beats a lot of beat the previous best algorithm to decode random linear code, but only in certain regime of parameter. And it turns out that the regime it attacked was not used by any it's not used by any how do you say by any scheme. For example, here when we did our analysis of Carrier and al., we studied the complexity of the algorithm at the Gilbert-Varchamov bound, and so it's basically it's at the hardest point, and so it's only used in signature. So okay, but the problem is usually they take rates that are 1/2, and our algorithm beats all the previous algorithm for rates that are smaller, in fact.
Does it Are the new estimates incorporated into the lattice estimator that everybody used to assess security levels?
Sorry, can you repeat?
The lattice estimator,
Yeah.
the Martin Albert estimator, do these things already incorporated in it?
So you mean the new analysis?
Yes. Yes.
No, because actually for now, there is no, so the state of the art now is just that Duca and Pool said that there was a problem, and so there is nothing which is out yet which solves this problem. So first, yeah, the first step would be to understand the BDD scores and then to say, okay, is there a problem? But actually, we had to change the attack by Carrier and Hall a bit to be able to, the attack, we had to change it. So I don't know if it was your question, but okay.
Um, Listing the speaker again, in the interest of time, can take questions offline.
Oh, pardon.
How do I screw it up? By removing my slides so that I don't do it?
Yeah, just don't press this.
Oh, is that not the laser?
Yes.
Okay. Thank you.
The next talk is on ideal SVP, hardness of ideal SVP, and the speaker is Benjamin Wesolowski.
Thank you. So this is a joint work with PhD student Joël Felderhoff, Alice Pellemari, and Damien Stellet. And I'm going to be talking about ideal SVP and how it's hard for small norm uniform prime ideals. So first, a few words on ideal SVP. What is it? I'm not going to be very long on reminding you what a lattice is, but still I want to define ideal SVP, and in particular the SVP part in it. The pointer is a bit wonky. Okay, so a lattice is described by a basis in a vector space, B1 up to Bn, and the lattice generated by this basis would be all the integer linear combinations of these basis elements. So here's an example. You have a basis, and all the points in the background are the lattice points. Now, SVP just asks you to find the shortest vector in this lattice, or the point that is closest to the origin other than the origin, or maybe not the shortest, but up to some approximation factor. So that's for the SVP part. Now, what's ideal about it? It's just that some lattices have something extra, some additional structure, which we call, which makes them ideals. So for example, look at polynomials with rational coefficients, Q adjoint X. That's a ring. And if you quotient it by the polynomial x to the n plus 1, for some n's, when n is a power of 2, say, that is going to be a field. So it's a field, which is also a Q vector space of dimension n. And in that vector space, you have lattices. One very special lattice is the one that you obtain if you look at polynomials with integer coefficients. Z adjoint x, quotiented by the very same polynomial. It is discrete, and it is in this vector space. It is a lattice in there. It's also a subring, because if you take two polynomials with integer coefficients, you get, and you multiply them, you obtain still a polynomial with integer coefficients. Now, this is a very particular example of an ideal lattice. More generally, an ideal lattice in K would be any lattice in K that is stable under multiplication by O. So a lattice A in K such that O times A is still in A. So you have different kinds of ideal lattices in there. An important family are the integral lattices, and these would be the sublattices of O that are also ideals. Now, among these integral lattices, you still have even more special ones, which are the prime ideals. And prime ideals are integral ideals that do not factor as products of other integral ideals, just like prime numbers. And they are really the building blocks for ideal lattices, integral or not. Any ideal lattice can be written as a product of prime ideals to certain powers. And when the powers are all positive, you get an integral ideal. And when some are negative, you get a non-integral ideal or a fractional ideal. So ideal SVP is just SVP in these special lattices. Why do we care about them? Ideal lattices have played and still play today an important role in lattice-based cryptography. They led to the first fully homomorphic encryption scheme by Gentry in 2009. And today they are still relevant in the analysis of practical crypto systems. They are still the simplest case of what we call module lattices that are used in the real world. Think Kyber and dilithium. And so they are important, but they're also very special. And this should raise some concern. Is SVP still hard in ideal lattices? Because now you've added all this extra structure and you may be concerned about making the problem simpler. And indeed, there are specific algorithms for SVP in ideal lattices that don't work generically. Still, ideal SVP is considered hard because even though we have better algorithms, they don't completely solve the problem. All they can do is reach slightly better approximation factors than we can do in generic lattices. So here we're interested in the hardness of ideal SVP. And more specifically, what's interesting for us for applications in cryptography is its average case hardness. So the question we ask is ideal SVP hard on average? And what we're aiming for is really some random self-reducibility. We'd like to prove that if we can solve ideal SVP for random instances, then you can solve ideal SVP in the worst case. And of course, for that question to be well defined, you need to state what it means to be an average or a random ideal. And for that, you need to specify a distribution. And really, there isn't one single good answer for that. And indeed, in the literature, we've seen several distributions considered. And for two of them, we already have random self-reducibility results. The first one was precisely used by Gentry. And he proved random self-reducibility for the following distribution. You look at the collection of all prime ideals. That's infinite. But now you put a bound on how large they're allowed to be, or how big their volume can be, or more precisely their norm. And now that's finite. So you can pick a uniformly random one. You pick a uniformly random prime ideal. Now you invert it. And this inverse of a prime is the ideal that Gentry is looking at. So he proves random self-reducibility for that, but maybe that's not fully satisfactory, because what you get is not an integral ideal. Maybe it doesn't feel so natural. Why did you have to take this inverse? So that's what works for Gentry's purpose. The reason being that he's not actually looking at SVP, he's looking at BDD, and the two problems are kind of dual to each other, and this duality implies that he's looking at inverses when we look at SVP. So not exactly what we want. Another interesting distribution was considered by BDPW20, where it is observed that if you look at the collection of all ideal lattices, it actually itself forms a geometric space. It's something that looks like a torus. Any point in the torus would be an ideal lattice. So you naturally have a geometry on that and a measure on that, which we call the Haar measure. And you could uniformly sample ideals according to that measure, and that would give you a random distribution on ideals. But that would be a continuous distribution. Problem, you can't really compute with actual continuous things, so you need to discretize that. And once you discretize, you run into some trouble because your discretization forces you to pick ideals that have a rather large norm. So this is very nice. It's geometrically canonical. You have a very rich mathematical theory around it that allows you to prove many things about this distribution. But now you have to deal with ideals of large norm, which is not exactly ideal. I'm not going to use that. I'm going to call this the first version P inverse ideal SVP, and the second version Haar ideal SVP. And the one we want, the one we're looking at, is the following one. You just pick a uniformly random prime ideal of bounded norm, just like when Gentry did. But now that's it. You don't invert it. You just use that one. And now it's integral, unlike Gentry, and it's of small norm, unlike BDPW. And these are two good properties you want if you want to compose this with other security reductions, in particular for ntrue. So this works well with ntrue, and it implies a link between ntrue and worst case ideal SVP. And I'm going to go back to that at the end of the presentation. So I'm going to call this version P ideal SVP for prime ideal SVP. Here's what we're doing. We're actually using Gentry's results. So he says worst case ideal SVP is no harder than P inverse ideal SVP. And now what we say is P inverse ideal SVP is itself no harder than P ideal SVP. An important caveat here is that these two reductions are polynomial time given a factoring oracle. So quantum polynomial time, classical sub-exponential time. And we don't know currently how to remove the need for this factoring oracle. So let's see how the second reduction works. we want a reduction from P inverse ideal SVP to P ideal SVP. So you're given as input the inverse of a prime, and you can assume that this prime has been sampled uniformly at random of bounded norm. What you're looking for is a small element in that ideal A, that inverse of a prime. And to help you, you assume you have an oracle that can solve that problem for primes instead of inverses of primes. So here are the main steps. First thing, you observe that you are being given the inverse of a prime, and you're looking for a small element in there. In particular, you have a prime, and you have an oracle that's good at dealing with primes. So maybe you can just do that. You feed your prime to your oracle, and it gives you a small element in there. Of course, that's not what you're looking for, because you want a small element in its inverse, not in the prime. So you're not done that yet. Second step is where everything's happening. And I'm not going to have time to detail how we do that, but here's what we're expecting it to do. We want a sample ideal algorithm that on input, an ideal and a small element in it, will return a pair by, where B is simply a uniform integral ideal of bounded norm, really just a random ideal independent of the input. Now Y is going to be a small element in BP inverse. So it sounds easy to generate uniform random ideals. It doesn't sound so easy to first generate the random ideal and then find a small element in that other ideal. And that's not how you're going to do it. Of course, think of it as some kind of trapdoor generation where you're essentially going to generate Y first and then find a B that suits it. And this is really the non-trivial part. It's where we need the factoring oracle. Third step, you're going to say, all I care about is primes. If B is not prime, I just abort. So there's a success probability here that is proportional to the density of primes. And luckily, we understand very well how dense prime ideals are among random ideals. Now you have B that is prime. And before you were sure it was prime, it was uniform among all ideals. So now it's uniform among all prime ideals. And that, again, is precisely what your ideal is good at dealing with. So you feed it to your ideal. To your oracle, sorry, and it finds a small element in B. So you find SB and B that is small. Now you found two small things, SB and Y. Take their product. SB was in B, Y was in BP inverse, so their product is in P inverse. And now why is it small? Simply because SB and Y are both small, so the product is small. And well done, we found a small element in P inverse. So these are the main steps of the reduction. The hard part, and yeah, most of the work goes into the second step and showing that you can actually do this sampling. Now let's go through the application to Entru. Entru was introduced in 1996, and in 2021, Pellemari and Stelle gave a carb reduction from ideal SVP to Entru, which means they give a translation. If you have an ideal SVP instance, you can turn it into an Entru instance. So that gives us a way to create Entru instances. If you have a way to generate ideals, turn them into Entru instances with their reduction. So we can do that with our distribution. Sample a uniformly random prime ideal P, feed it to this carb reduction, you get an Entru instance. And you can do that carrying along also a trapdoor. And we call this distribution D-Entru. By construction, thanks to their carb reduction, we have that solving Entru for that distribution is at least as hard as the P-ideal SVP problem. And now the P-ideal SVP problem we know is at least as hard as worst-case ideal SVP. So we have a connection between Entru for some distribution and worst-case ideal SVP. This is in fact the first distribution over Entru instances with a polynomial modulus whose hardness is supported by worst-case lattice assumptions. And you could not do that with the previous reductions because the norms would be too big or the primes would not be integral. The obvious caveat here is that to do this reduction, to sample this distribution, you would need a factoring oracle, which we don't have. So open question here, can you remove the need for this factoring oracle? Thank you for your attention.
Very nice. I was wondering, have you looked at all into for sort of concrete parameters that we want to run Entru for, whether the factoring is actually something that's feasible, or because we also don't need, to generate a ton of them, right?
No, we haven't looked at what practical sizes of parameters that would be. Indeed, factoring random integers is not always hard.
Yeah.
It will depend on what integer you have. And for many of them, it's going to be easy. And if the numbers are not so big, it may always be feasible. But yeah, I have no clue what it would look like for concrete parameters here.
Okay, thanks.
Okay, let's thank the speaker again. The next talk is about the multi-user security of LWE-based non-interactive key exchange by Roman Langer.
Thank you for the introduction. Let me start with a brief recap what non-interactive key exchange, or for short NIKE, is. It's a cryptographic primitive that allows any pair of users to obtain a common shared secret key using a public key infrastructure. So in more detail, we have a setup algorithm that outputs public parameters, which can be used by every user to generate its public secret key pair. And then any pair of users, so for example, Alice and Bob, then Alice can use her secret key and Bob's public key to compute the shared key, and Bob can use his secret key and Alice's public key to compute it, and they should be the same. A famous example for this is the Diffie-Hellman key exchange, but this talk will be about an instantiation from the LWE assumption. And for this, we have to slightly relax the notion of NIKE. So we ask these shared keys to be the same only with high probability. The most basic security definition for NIKE is light security. There the adversary gets the public key of two users and a real or random shared key between them. And his goal is to distinguish these two scenarios. However, this security notion only really captures scenarios where a public key is used just once, so to compute one shared key. A more realistic security notion is adaptive honest key registration, for short HKR security. And that is defined via a game in which the adversary can adaptively create new users. He can corrupt users, so that means he gets their secret key. He can reveal shared keys between any pair of users, and he can do the challenge as before, so select two users and then gets a real or random shared key. An even stronger notion is adaptive dishonest key registration, for short DKR security, where the adversary gets one additional power, and that is to introduce maliciously generated public keys. So that means he can generate public key maliciously, and then in particular ask for shared keys that are computed with, for example, a challenge user's secret key. Adaptive DKR is probably the most realistic security notion and also the strongest. This implies adaptive HKR, which implies light security. It was shown before that light security also implies adaptive HKR security for NIKEs that have a negligible correctness error. And in this work, we show that this negligible correctness error is necessary for a generic argument. It was also shown before that if you add a NISIC proof of knowledge of the secret key to every public key, you can get from adaptive HKR to adaptive DKR security. However, that works only for NIKEs with perfect correctness. And the results from this work also imply that this perfect correctness requirement is necessary here. Okay, now let me get on how you get NIKE from LWE. So the public parameters is a random square matrix. And Alice and Bob now both sample a short LWE secret. So for example, a binary distribution can be used, and a noise vector, typically a discrete Gaussian. And Alice will multiply her secret from the left-hand side to this matrix A and add the noise, and that's her public key. And Bob will do the same, but multiply his secret from the right-hand side to this matrix A. And the secret key is always the LWE secret. So you notice there's a slight difference between how Alice and Bob generate their public keys. to get a full-fledged Nike where every pair of users can generate or compute their shared key, every user, in fact, has to generate an Alice type and a Bob type public key. So how do they obtain the shared key now? That works as follows. Alice computes the inner product between her secret key and Bob's public key. And for security reason, she also adds some noise to it. And Bob does the same thing. So he computes the inner product between Alice's public key and his secret key and adds some noise. And then they get the terms that are here on the slide. And if you look at the black part, that is the same. And that is a large value because the entries of A are large. But there's also this red part, which is different. However, the red part is short because both the secret and the noise is short. So these values are approximately the same. And by simply rounding these values, we can get the shared key that is the same with high probability. So if you use a polynomial modulus to noise ratio, this means you get a non-negligible correctness error. And if you use super polynomial modulus to noise ratio, you can get a negligible correctness error. And there's an impossibility result by Guo et al. That shows that this correctness error is really hard to avoid. However, I think the Nike is still useful despite this correctness error. For example, because there's a protocol that allows you to correct this correctness error with just one bit of interaction. So what about the security of this Nike? Well, the first works by Ding et al. And Peikert proved only light security. We've seen before that with this generic arguments, that means for super polynomial modulus to noise ratio, we also have adaptive HKR security. And until recently, there was nothing known about the empty parts of this table. A concurrent work to this showed that a variant of this Nike that also uses the QROM model and can achieve adaptive DKR security. In this work, we show that for a bounded number of users, you can get adaptive HKR security even with a polynomial modulus to noise ratio. And we also show that with the polynomial modulus to noise ratio, the Nike is not adaptive DKR secure, even if you add these NISIC proof of knowledge. And for super polynomial modulus to noise ratio, we show that if the noise you add to the shared keys is only polynomially larger than the noise you use for your public keys, it's still insecure. But if the noise is super polynomially larger, it becomes secure. Okay, now let me briefly recap how the light security proof for this Nike worked. So in the light security game, the adversary gets all these parts that are marked here in blue. And security proceeds via hybrid argument. In the first step, we switch Bob's public key to something uniformly random, which is a straightforward reduction to the LWE assumption. And in the second step, we switch Alice's public key to uniformly random. And more importantly, we also switch this value KAB to uniformly random. And this works by applying the LWE assumption to a matrix that has as top part this matrix A and as bottom part the public key of Bob. So what's the problem with getting adaptive HKR security? Well, the reduction can just guess the two challenge users. And then there's actually only one thing left to do. And that is the shared key queries where a challenge user's secret key is used. So for example, assume that Alice is again a challenge user and the adversary asks for the shared key with Charlie, but Alice's secret key should be used to compute this. So he gets this value round of KAC. Then it seems the reduction needs to know this value KAC, which can only be computed with Alice's secret key, and we have to avoid that to use the argument from before. The reduction can, of course, compute KCA, so the shared key compute with Charlie's secret key, but they are slightly different, so they differ in this red part. And our idea is to use the leakage resilient of LWE to make the reduction just know these red parts. So the first part is leakage about the secret, which can be justified, for example, by a result from Brakersky and Döttling. The other part is leakage about the error. And for this, we use a result from Döttling et al. From Eurocrypt, that shows that noisy linear leakage about the arrow is okay. And this works fine here because we anyway have the noise for the shared keys. This way we can get multi-user security, but the LWE dimension n now has to grow linear with the number of users. So this is better than the trivial solution to use a public key, a new public key for every shared key, but it's not that much better. This really becomes useful with our second trick to reduce the amount of leakage. And the idea is quite simple. The adversary actually does not get this value KAC, he only gets the rounded version, round KAC. And quite often, these rounded values, round of KAC and round of KCA, are the same, and then we don't need any leakage. So if you imagine, for example, that the rounding function looks like this and rounds everything here that's on the right-hand side to the bit 0 and everything on the left-hand side to 1, then if this value KCA is quite far away from a rounding boundary, then we don't need any leakage. But when it's quite close to a rounding boundary, then we do need the leakage. And to get this into a formal argument, there's one challenge, and that is that the leakage on the secret must not depend on the matrix A. However, whether KCA is in this red zone close to a rounding boundary or not clearly does depend on A. However, we observe that the leakage we need is SA transpose times EC, and EC has only very small influence on where KCA is. And this can be turned into an argument that avoids this dependency on the matrix A. So this way we get multi-user security where the number of users can grow polynomially in n, and this polynomial depends on the modulus to noise ratio. Thank you.
Questions for the speakers? Okay, let's thank the speaker again. Yes, the last talk of the session is about revocable cryptography from learning with errors, and it will be given by Prabhanjan Anna.
Okay, so I'm going to be talking about revocable crypto and how we can build it from learning with errors. This is in joint work with Alex Brumba and Vinod Venkatanathan, both from MIT. So quantum computing can be both useful and harmful to cryptography. In this talk, we'll see how it can be useful to cryptography. Specifically, we're going to focus on the area of unclonable cryptography, which is about how to leverage the no-cloning principle of quantum mechanics to build crypto primitives that are impossible to achieve classically. So roughly speaking, the no-cloning principle says that it should not be possible to clone arbitrary quantum states. And this is not a new area, and it has been there from the 80s. The very first primitive that was introduced was quantum money by Weissner. It's arguably one of the most popular primitives in unclonable cryptography. And since then, there have been many interesting unclonable primitives, including unclonable encryption, copy protection, which I'm going to briefly talk about now, certified relation, software leasing, and so on. Okay, so let me talk about what copy protection is all about. So roughly speaking, copy protection is about leveraging the no-cloning principle to achieve software antipiracy, meaning that I'm going to associate software with quantum states in such a way that you should not be able to clone and produce many copies of this software state. And formally speaking, the way we define security is in terms of a tripartite adversary. There is Alice, Bob, and Charlie. Alice receives a software state that is obtained by applying this copy protection function, and then it produces a bipartite state. So what we want is that both these parts, which could be entangled with each other, should not be used to replicate the original functionality. So in other words, if I compute Bob and Charlie on inputs XP and XC sampled from some distribution, then the probability that they win, which is when the outputs are match the outputs of the function, the probability that they win should be low. So this notion was first introduced by Aronson in 2009, and since then it has been an important problem in quantum cryptography. It was open for a long time how to achieve copy protection, and very recently we showed that for some contrived unlearnable functionalities, copy protection is actually impossible to achieve. And for some interesting cryptographic functionalities, we do have some positive results. So for instance, random functions, decryption functionalities, signing functionalities, and so on. But the problem with all these feasibility results is that they assume I/O. And while there has been remarkable progress in constructing I/O, we still don't know how to achieve post-quantum secure I/O from concrete cryptographic assumptions. This is still a challenging open problem. So it will be interesting to see if we can actually minimize the assumptions in these constructions. But it turns out that even this is a long-standing open problem in quantum crypto. So for instance, if you're able to remove I/O from some of these applications, then you get public key quantum money without I/O, which is a very important problem in quantum crypto. So what we are going to do is, while we are hoping to build I/O from concrete assumptions, we should also try to look for weaker security notions of copy protection that are still meaningful and that we can achieve it from better cryptographic assumptions. So this is our research agenda to initiate this area called as revocable cryptography, which is weaker than copy protection, but it turns out that we can build many of these things from learning with errors. And we study many primitives such as public key encryption, full homomorphic encryption, random functions, and so on. Okay, so let me first briefly describe what revocable public key encryption is. This is a regular public key encryption scheme, except that I also associate decryption key with a quantum state. So there is an additional security guarantee that we need from revocable public key encryption, which is the following. So there's a challenger who gives the decryption state to the adversary. So the adversary can use this decryption key state to decrypt how many of our ciphertext it wants. And after some time passes, the challenger will ask the adversary to return back the state. Note that this is sort of an inherently quantum phenomenon. So for instance, if this was classical, it doesn't make sense for the challenger to ask the adversary to return back the state. Whereas, due to the no cloning principle here, it makes sense for the challenger to ask the adversary to return back the state. So informally, what we want is that once the adversary returns back the correct state, it loses the ability to decrypt ciphertext. Specifically, what we want to say is that it should not be possible for the adversary to simultaneously return back the correct state and break semantic security. Or rather, they should only hold with negligible probability. And if you're familiar with software leasing, this is finite term key leasing, except that we also allow the adversary to be malicious in the last phase. Okay, so let me give the formal definition very briefly. So again, this can be thought of in terms of similar to the copy protection security guarantee. The challenger gives the decryption state to the adversary, Alice. The Alice returns back the state. Once the adversary returns back the state, I'm going to apply this measurement, this projective measurement that just checks if the state returned back is the correct state or not. And then simultaneously, I also ask the adversary Charlie to break semantic security. So I give him either encryption of 0 or encryption of 1, and I want Charlie to tell me which ciphertext I gave him. Okay, so security guarantee just says that it should not be possible to simultaneously revoke and break semantic security. Revocable pseudorandom functions is defined similarly. I have something called as an evaluation key, which is a quantum state using which I can still produce the outputs of this random function. The only difference is that instead of Charlie breaking semantic security in public encryption, here he is distinguishing whether he gets the output of a PRF or something uniformly at random. So Y0 here corresponds to the output of the PRF on X, Y1 corresponds to something picked uniformly at random. So we have a similar guarantee here as well. Okay, so what do we show? We show that assuming some conjecture that I'm not going to define, you can look at our ePrint version. So we show that dual Regev public encryption is actually key revocable. And assuming the same conjecture, we also show that the dual GSW fully on-freq encryption is key revocable. And we also come up with a new construction of pseudorandom functions, and we show key revocability of it, again, assuming the same conjecture. So I should mention a very interesting and exciting concrete work by Agrawal et al., who showed that there exists some public key encryption that is key revocable, assuming any post-quantum secure public key encryption. So the difference is that we wanted to study like key revocability of dual Regev encryption, whereas they come up with a new encryption that is tailored to be key revocable. But this work doesn't study the other two results. For instance, the fully homomorphic encryption was not even studied in the copy protection setting. So this is something new. And also for pseudorandom functions, copy protection of pseudorandom functions was studied, but it was based on I/O, whereas we can show how to construct the same without using I/O. So we also study a stronger notion of key revocability called as classical revocation. So here, instead of returning back the state, I actually return back something classical. So I perform some deletion operation on the state, and I get something classical, and I return back the state, I return back the classical string. And the requirement is that the classical verification algorithm and the semantic security should not simultaneously hold. Okay, so we get the same results based on a slight variant of the previous conjecture, but the advantage is that all these different results have classical revocation. Okay, so let's look at some high-level ideas about how to achieve revocable public key encryption. So again, we start with dual Regev encryption that we are all familiar with. So the public key is an n cross m matrix. Here it is denoted by a bar. You should think of m to be at least n log q. And then I also going to pick an m-dimensional vector y. And in the dual Regev encryption, the decryption key is some short vector x says that a times x equals, or a bar x equals y. But here we need a quantum decryption key, and the quantum decryption key is very simple. What I'm going to do is I'm going to consider a superposition over all the short solutions that map A to Y. Okay, so specifically, we consider a superposition where the weights correspond to the truncated Gaussian with mean 0 and sigma, which is standard deviation, is going to be something like poly in M. Okay? And the encryption algorithm is the same as before. So in order to encrypt, I'm going to compute s times a plus some noise vector. I'm going to denote this using this approximate symbol. And then I'm going to also compute s times y. I'm going to shift s times y with some message times q over 2. So you can see that using a classical decryption key, you can decrypt and recover mu. Using the quantum decryption key, also you can recover mu. The way you do this is just to run the classical decryption algorithm coherently on the quantum state. Okay, so this is the dual Regev encryption. So how do we show that this is secure? So I want to give some ideas. I will not be able to fully sketch the proof. So I want to show that you should not be able to simultaneously return the state and break semantic security, right? Okay, so now suppose let's say he returns the state. Then we want to argue that he cannot break semantic security anymore. The other extreme case is maybe he keeps the state, in which case we want to say that the revocation doesn't succeed. But of course, he can do something more complicated. He can do some convex combination of these two strategies, and we want to even rule this out. So to give some intuition, what I'm going to do is I'm going to forget that he has to return back the state. Okay, so let me just focus on semantic security for now. How do you argue that semantic security holds? Again, we want to show that encryption of 0 is indistinguishable from encryption of 1. And if you open up the ciphertext, you have s times a, s times y, versus s times a, s times y plus q over 2. You want to show that these two are indistinguishable. So what we are going to do is we are going to first apply the Gaussian collapsing lemma, which says that either I give you the state or I give you something that is obtained by measuring the state in the computational basis. And you should not be able to distinguish which are the two cases you're in. And we're going to first apply this lemma. Once we apply this lemma, we collapse the state psi y to be some classical string. And once we do that, then things become more classical. That lets us use existing techniques that were explored in the leakage resilience of learning with errors to argue that you can, the indistinguishability of CT0 and CT1 boils down to something like a Goldrake-Levin problem over FQ. So it boils down to distinguishing the inner product of U and X0 versus U and X0 shifted by this QO2. So once we do that, we apply what is called as quantum Goldrake-Levin or large finite fields to extract X0. Okay? So X0 is some short solution that maps A to Y. Okay, so let me quickly wrap this up. So the problem is now we have to argue that this simultaneously holds. So we can extract simultaneously well when the revocation is succeeding. And we don't know how to do this just assuming learning with errors. That's why we need this new conjecture to let us get to this point. Okay. So once we do the conjecture, then what we're going to do is, instead of measuring the state using this projective measurement M, what we're going to do is we're going to measure the state in the computational basis. It turns out that if earlier the adversary was succeeding with inverse polynomial probability, it still succeeds with inverse polynomial probability even if you measure in the computational basis. And once you do this, you're almost done because you have two short solutions, X0 and X1. They both are short, they're different, and you can use this to break SIs. This is how we prove semantic security. And since I don't have time, I'm not going to be talking about FHE and pseudorandom functions. I just want to mention that proving revocability of FHE is easy because we are working with dual Regov encryption. We just sort of look at the dual version of GSW, and we can easily argue. For pseudorandom functions, we had to come up with a new tailored construction and prove it to be key revocable. But both FHE and pseudorandom functions, we argue security by reducing it to the security of dual Regov public key encryption. Okay, so just to conclude, we come up with weaker notions of copy protection that we can base it on assumptions that don't involve I/O. So since our work, there has been a follow-up work that comes up with another construction of public key encryption, FHE with classical communication, assuming just LW, they don't need the conjecture. But that still doesn't solve the problem that we set out to solve, which is to prove that dual Regov encryption is key revocable. That's still open. It would also be interesting to look at revocation for other functionalities. And an even harder problem is to come up with copy protection for interesting functionalities from just learning with errors. This I conclude.
Any questions for the speakers? Well, let's thank all the speakers of this session. And we can head over to the coffee break outside.
下一场是
I'll go through everything if that's okay. Yes, sure.
Okay, so let's start the session. We have an exciting session on quantum cryptography. The first talk is by Kwak Yu on how to achieve public key encryption from one-way functions using quantum resources.
Thank you for the introduction. So hello everyone. Today I'm going to be talking about our paper public key encryption with quantum keys. And this is joint work with Kapsaja, Alex, Luis, Julio, or and Michael. So let me start with some motivation questions. So we saw this picture on, I think in the first day of the conference. So this is two cryptographic ones in the Imperials 05 ones. So we have mini crypt where we have one-way function and cryptomania where we can do all the amazing public key cryptography. And there's some black box separation between the two ones. And this picture changed dramatically when we consider quantum computation and quantum communication. In particular, two works, the first one by Grillo and then Patrizia, and they show that using quantum computation and quantum communication, you can do several cryptomania primitives using only one-way function. And then people start asking the question, can we even go lower? So for that, let me recall the notion of pseudo random state generator, which you already saw yesterday in the invite talk. So basically, PRS or pseudo random state generator is a quantum algorithm that take input a classical string X and output an quantum state psi X. That is computationally indistinguishable from a hard random state. And in 2021, Christmas showed that one-way function cannot be constructed from PRS in a black box way relative to some quantum oracle. So that shows there's also some separation between one-way function and PRS. And for the application, it's more useful to consider an variant of PRS, which is pseudo-random functionalized state, introduced in 2021 by Anat Q and Yuan. So PRFS, now the algorithm G also has some secret key K, and the output depends on both the classical string X and the secret key K. So using the notion of pseudo-random state, random state generator and its variance, a series works so that you can do a lot of crypto even without one-way function. So the name of this one is we call it micro Q crypt. I think it's suggested by Murime. And so if you see on the picture, so again, there's some kind of black box separation between micro Q creep and mini Q creep. And if you see on the picture, then there's one remaining object in cryptomania has not been addressed before, which is public key in question. And so in this work, we ask the question where to put the quantum public key in question. So in this work, we initiate the formal study of quantum public key encryption, or QPKE. So we define, we give the definition and the security notion for QPKE with different flavors. And then we give several construction for QPKE with quantum public keys from one-way function or even from weaker assumptions. And then we also answer the question whether we can achieve unconditional security for QPKE, because in the quantum setting, the close related notion, which is to public key encryption, which is a key exchange. We know that we can achieve key exchange unconditionally by the famous protocol QKD protocol. So in this work, we saw that it's also impossible to achieve unconditional security for QPKE using shadow tomography techniques. And we also want to point out that there's another proof using the quantum Sanubao pointed out by Takashi Zamakawa, but that proof is more less direct and is used more new quantum cryptographic primitives. So let me go to the first part of the talk, which is the definition. So QPKE, the definition of QPKE is kind of straightforward. It's just the same as classical public key encryption. We have the key generation, we have the encryption and decryption. So few differences. The first one, for the encryption, the ciphertext can be either classical or quantum state. And for the key generation, the first thing that the secret key is a classical string, just like in classical public key encryption. But the public key can be either classical or quantum state. And in our work, if we only consider for the case where the public key is quantum state, we require it to be a pure state. And I will explain the reason that why we consider this notion later. So for the security, we just follow the standard semantic security paradigm, where basically the adversary cannot distinguish the encryption 0 and 1, except that the adversary now also given a polynomial many copy of the public key. So the reason is that because in 0, we expect the public key to be unclonable if it's a quantum state. So that to make the security notion to be meaningful, we allow the adversary to obtain polynomial many copies of the same public key. And also, if the public key is pure state, then this implies a non-trivial way to distribute the quantum public keys. So that's actually suggested by Gosteman in 2005. So the idea is we can use swap tests to compare the public key with different certificate authorities. However, we know that this approach only achieve inverse Pauli soundness, and I will be, talk more about that at the end of the talk. So let me give you a quick glimpse of our construction from one-way function and from PIFS. So for the full, so those are really simplified version of the constructions that we give in the paper. So for the first one, from the one-way function, for the key generation, is simply the secret key is just simply an PIF key, and the public key is uniform superposition of own evaluation of the PIF under the SK. And for the encryption, the first step we just measure the public key in the computational basis to get a pair classical strings X and Y. Y is the image of X under the secret key. And the idea is now we can use Y as the secret key for some symmetric key encryption that we can build from one-way function. And X is a hint that if we have the secret key, we can recover the value Y. And the decryption is quite straightforward. As I said, you know the secret key sk, you can recompute y from x, and then with y you can decrypt. So the intuition for the security proof that if you don't have the secret key sk, then basically you can make y to be uniformly random string. And if y is a uniformly random string, then we can reduce the security of this scheme to the security of underlying symmetric key encryption. And the construction from PIS, that the one that I present here, follow the same method. So for the key generation, you answer the secret key for the PIS, and the public key again is just uniform solution of the PIS. And the encryption now, instead of measuring the whole public key, we only measure the first register, the X register, to get a classical string X. And after the measurement, the public key just collapses to the psi k skx. And for the encrypt, to encrypt 0, we just return this pair of x and psi skx. Otherwise, we return x and then maximally mixed state. And for the decryption, we using some useful property of PIFS. You can verify if the quantum state that you receive from the ciphertext is indeed psi skx or not. And from that, you can do the decryption. And again, the security proof for this construction also follow the same approach that I just present for the one form one wave function. So that is the two construction that simple construction. And in the paper, we also give more involved construction achieving CCA security or construction from more assumptions than just PIFS and one wave function. So for the last part of the talk, I will present a quick proof for the impossibility reason. So the main observation is that for, let's say you have PK0, which is the honestly generated public key, then the observation is that for any other blue PK, if PK0 and PK blue they are close enough, then you can use the corresponding secret key of PK blue to decrypt any ciphertext that encrypted with PK yellow. So that is so here's the formula for this statement. And then the next step, we only need to we need to estimate on the distance of PK yellow and the distance for all possible PK blue with PK yellow. But here's the crucial point that we only given polynomial many copy of PK yellow, and that prevent you from the trivial brute force. And the technique we use is to use shadow tomography to estimate this value and find the appropriate SK that can use to decrypt the ciphertext and break the security. So to conclude, in this talk, we present the definition of quantum public key encryption. We saw several impossibility and possibility for constructing QPKE. And we know that there's some caveat. So first, our construction will be broken if the others can modify the quantum public key before the encryption. And a single copy of the public key can be used only by one encryptor. So there are two open questions. The first one is how we can distribute quantum public keys to achieve negligible soundness, for example. So this have been partially shown in follow-up works. And I think the more interesting question is to study the possibility or impossibility of reusable QPKE, where one public key can be used by many encryptors, just like in the classical public encryption. And for that, I conclude my talk, and thanks for your attention.
Questions?
In your construction of the PKE, if you can show the slide, this involves like this one. This involves summation over the domain of the PRF, and classically it would be very expensive. Do you have an efficient way of creating such a state?
You can easily compute the PK. First, you put uniform superposition on X that you can just do by applying Hadamard on zero state. And then you evaluate the PIF coherently in superposition, and that you would give you this state. That's answer.
Thank you.
Any other questions? I have a question. So you talked about reusability of your construction, right? Don't you already get reusability? Once you measure, you get XY. Can't you use XY to encrypt many ciphertexts?
So basically, you can in the construction that we we give in the paper, you can reuse X and Y to do many encryption, but like X and Y has to be kept secret now.
Oh, I see. Okay, so there are no more questions. Let's thank the speaker again.
Thank you.
Okay, so the next talk is one out of many unclonable cryptography by Fuyuki Kitagawa and Ryo Nishimaki, and Ryo will give the talk.
Thank you for the introduction. So I'm going to talk about one out of many unclonable cryptography. This is a joint work with Fuyuki. So this is a short summary of our work. We propose new definitions for unclonable cryptography. This is a relaxed variant of indistinguishability-based unclonability. And we also propose construction of unclonable secret key encryption in the standard model under this relaxed definition. We also propose unclonable predicate encryption and copy protection for single bit output point functions. And we also propose single decryptor encryption in the standard model. This is under the standard definition. Okay, so let's see what is unclonable cryptography. In this talk, in this talk, I focus on unclonable encryption. So first of all, it is easy to copy classical information. So say Alice wants to store her encrypted file on the cloud server. And after that, Alice, when Alice downloads the encrypted file, the cloud server may keep a copy of the encrypted file. It is impossible to prevent copying digital information by using classical cryptography. However, if we use the power of quantum computation, we may be able to prevent copying quantum information due to the no cloning theorem. So Broadbent and Rod introduced the notion of unclonable encryption where ciphertexts are quantum state and copy protected. The syntax of unclonable encryption is the same as standard encryption. This is a security game of unclonable encryption. First, the adversary sends two plain text to the challenger, and the challenger flip a coin and send a challenge ciphertext to the adversary. And then adversary 0 generate quantum state over two registers and send the first and second registers to adversary 1 and 2 respectively. These two adversaries cannot communicate each other. After that, the challenger sends the decryption key to these two adversaries. And then they output a guess for the challenge ciphertext. If the probability that these two guesses are correct is less than half plus negligible, then we say that this is unclonable unclonable indistinguishability. So let's briefly see the previous works. Broadbent and Rod presented the first unclonable encryption scheme that satisfies one unclonable one-way secure unclonable one-wayness in the standard model. And Anand Karaoglu improved their scheme. Later, Anand Karaoglu, Lee, Liu, and Chandri presented the first unclonable encryption that satisfies unclonable indistinguishability in the quantum random oracle model. And Anand Karaoglu, Liu also improved their scheme. So the big question in this area is, can we achieve indistinguishable secure unclonable encryption in the standard model? In this work, we construct unclonable encryption in the unclonable indistinguishable secure unclonable encryption in the standard model, but under the relaxed definition. We construct this scheme from the standard assumptions, LW assumption. Okay, so let's move to the new definition called one out of many unclonability. So the first part of this game is the same as the standard unclonable indistinguishability. But adversary 0 now generate a quantum state over any registers and send send each state to each adversary of the next stage. And the challenger now randomly choose alpha from 1 to n and send the decryption key only to adversary alpha, not all adversaries, only alpha. And this adversary alpha output a guess B star. And if the probability that the guess is correct is less than half plus 1 over 2n plus negligible, then we say that this is one out of many unclonable indistinguishability, satisfy unclonable indistinguishability. We can derive this trivial bound as follows. So if the adversary 0 passes the challenge ciphertext to say adversary 1 as it is, then adversary 1 can win this game with probability 1. Yeah, the other adversaries can output a correct guess with probability half. So we can derive this trivial winning probability. And this security means the following. So the adversary cannot generate n copies with probability 1 over n plus delta. Why? So if the adversary can do this, then the adversary can win this game with if adversary succeed in generating n copies, then the adversary can win this game with probability 1. And if the adversary do not succeed, still they can output a correct guess with probability half. So we can derive this this bound. But this probability is probability contradict to the security of one out of many unclonability. So the adversary cannot succeed in generating n copies with probability 1 over n plus inverse polynomial. And I briefly explained the interpretation of new definition. This definition roughly says that the expected number of successful copied quantum object is almost equal to 1. Why? Let's see this for n equal to 2 case. So suppose that we check we consider a slightly different game, but this is equivalent to the definition what I explained in the previous slide. Let's assume that we check adversaries. Both adversary A1 and A2 output guesses, and we check only one answer. And then the success probability, we can interpret the success probability like this. So here, P sub CC is the probability that both answers are correct. And P sub IC means that A1 is incorrect and A2 is correct. P sub CI is the inverse of P sub IC. Okay? So we check only one answers of these two adversaries. So we can write the security success probability like this. And so, by the way, the standard unclonable indistinguishability says that the expectation of P sub CC is less than half plus negligible. And we can rewrite this inequality by multiplying 2. We can obtain this inequality. The left-hand side means that the expected number of correct answer. So we can say that the expected number of correct answer is less than 1 plus half plus negligible. We can easily generalize this to general case n case. So this said that the expected number of correct answer is less than 1 plus 1 over n plus negligible. So if n is large, this is almost equal to 1. And so there are a few related works. Behera Satas proposed a similar security definition for quantum money with a similar security flavor of this notion. And Aronson also proposed the definition for copy protected program by focusing on expected number of successful copies. Now, let's move to how to achieve our one out of many unclonable encryption. So first, we can show that one out of many unclonable encryption is equivalent to one out of many single decryptor encryption, which is a copy protected version of public key encryption. We can prove this equivalence by similarly to the result by Georgia and Chandri. Note that here, GZ20's SDE is different from CLLZ21's SDE. And next, we can show that one-time strong anti-piracy SDE implies one out of many SDE. The technical core of this result is the next part. We can show that a single key and succinct key ciphertext policy functional encryption implies one-time strong anti-piracy single decryptor encryption. We use, interestingly, we use watermarking extraction technique to achieve this result. One good feature of our construction is our scheme support multi-bit plaintext. Although Anand, Karaoglu, and Liu presented one-time single decryptor encryption without any assumptions, but this only supports a single-bit plaintext. Note that we cannot use a standard parallel repetition and hybrid argument in the unclonable setting. So we don't know how to expand the plaintext space in our setting. And we can construct our single key, succinct key ciphertext policy FE by using hash encryption and garbled circuit. These tools can be instantiated with the standard LW assumption. So we can achieve our construction by using LW assumption. How many minutes I have? Okay. Okay. So I don't have much time, so let me skip the construction. Please see the paper for the detail. And I want to say that we also achieved copy protection for single bit point function and unclonable predicate encryption by using unclonable encryption. this is a general construction. So if the underlying unclonable encryption satisfies the standard unclonable indistinguishability, the resulting construction also satisfies the standard unclonability. Okay, let me summarize my talk. We propose new definition for unclonable cryptography, and we also constructed one-time secret key multi-bit single decryptor encryption from the LWE assumption. So we can obtain the one out of many unclonable indistinguishable encryption from the LWE assumption. That's all. Thanks.
Any questions from the audience? I have a question. So do you know if you can construct one out of many copy prediction for other interesting class of functionalities like random functions and so on from assumptions weaker than IO? Because that is something that is still sort of open, right?
Yeah, yeah, I think so.
Okay, okay. Oh, yeah, okay.
So your construction of single decrypt encryption, like you said, we have also a construction of single decrypt encryption in the usual definition, not the one out of many definition.
Our single decryptor encryption is under the standard definition, not the one out of many definition.
So it doesn't follow from the schema you showed for the one out of many, right? Like the schema.
Are you saying that we get
yeah, in this picture.
Okay, yeah. No, so yeah, we can get one out of many unclonable encryption, but so here there is not. ZZ20's SDE is different from CLZ21's SDE. So our SDE is under the definition by CLZ21. Okay. So this equivalence result doesn't hold for the CLZ21 definition. So we cannot go to the one unclonable encryption under this definition.
Sure, but I'm saying the single decrypt encryption construction, which is in the usual definition, that is not part of this schema at all, right? Or it's completely independent? Like you have here one out of many single decrypt encryption, right? But you also have a construction which is not one out of many, which is the usual thing, and that is completely different from this.
No. So not completely different because one-time strong anti-piracy SDE implies one out of many SDE. So the construction is the same.
So this is your...
Yeah. We constructed this one. We construct this one. So immediately imply one out of many SDE.
So this one-time one is the construction in the usual definition.
One-time construction.
I see. Okay.
Yeah.
Yes, we don't have time for more questions. Let's thank the speaker again.
Thank you.
Okay, so the next talk is about how to achieve copy protection for non-trivial functions in the plane model and with classical communication. And Paul is going to give the talk.
Okay, thanks for the introduction. So hi everyone, I'm going to talk about semi-quantum copy protection and more, and it is a joint work with Céline Chevalier and Rui Vu. Before talking about semi-quantum notion of copy protection, I will briefly recall what is copy protection. So it's a primitive in which you have a quantum vendor on the left that will pick a function f from a family of function and protects this function using a protection algorithm to get a quantum state that is a quantum protection of f. Then he will send this quantum protection to the client, and with this protection, the client will be able to evaluate this function on any input x. And roughly speaking, the security of this primitive says that any malicious client cannot split this quantum protection to get two quantum states that can be used both to compute
to evaluate the function f. So in this setting, as I said, the vendor is quantum, and he communicates with the client using quantum communication. And the semi-quantum copy protection is the setting in which the vendor is classical, and so he has to communicate with the clients using classical communications. And then what he has to do is to classically instruct the vendor on the client, sorry, on how to construct this quantum protection of f while preserving the security of this primitive. And so how to do this kind of a primitive? So first, I want to mention that in a lot of copy protection schemes in the literature, the quantum states that are used are coset states. So a coset state is can be seen like is this state here, and it can be seen as given a subspace A and two vectors n and s prime, the superposition over all the vectors in A plus S, and in some way also the superposition over all the vectors in A perp plus S prime, which I would call the dual coset. And from these quantum states, it's easy to get a vector in the regular coset by just measuring in the computational basis. And it's also easy to get a vector in the dual coset by measuring in the diagonal basis. But it's impossible to get a vector in both of these cosets. And this is due to the destructive properties of quantum states. And this property is called the direct product hardness. But actually, in order to build our copy prediction schemes, we will need something a bit stronger than that, which is called monogamy of entanglement. And so monogamy of entanglement is another property of coset states, and is captured through this game in which we have a challenger sending a quantum state to Alice, which will have to split this quantum state into two quantum states, sigma 1, sigma 2, that can be entangled. And then we'll have two other adversaries, Bob and Charlie. Each one of them will get a piece of a share of this quantum state, sigma 1 or sigma 2, and will be given also the description of A. And they will have to, for Bob, output a vector in the regular coset, and for Charlie, output a vector in the dual coset. And this has been proven by Kolf and Vidic to be impossible to win. But yeah, what is important is that for constructing our copy prediction schemes, we will ultimately need to reduce to this game. And because we want semi-quantum version of this scheme, we want a semi-quantum version of this monogamy of entanglement game, meaning that now the challenger will classically instruct Alice on how to construct a random coset state while preserving the hardness of this game. And this is actually the main contribution, the main technical contribution of our work is how to construct such what we call a remote coset state preparation between a challenger and Alice here. So I will give a quick overview of on how we construct this protocol. So we'll combine two protocols, one which is a quantum FHE-based coset state preparation, which is very similar to what we want to have, but the one we will use have a weaker security than what we want to get. And in order to overcome this weaker security, we will combine it to a so-called self-testing protocol of BBA84 states. I will give a bit more details on what is self-testing later, but the idea is that the protocol that we use for BBA84 is for BBA84 states, which are simple states, and we want to have the same kind of protocol but for coset states. So we'll combine these two protocols and get this self-testing of coset state protocol. But this is not completely over because we want to have, like in the self-testing, we don't have any state in the end. So we want to have, we will need to slightly modify this protocol to get a remote coset state preparation, which is what we want to have ultimately. So first I will describe this quantum FHE-based coset state preparation by Schmeli in 2022. So it's based on quantum FHE, and yeah, a bit of notation before. So whenever I write X or anything else on a yellow square, it means that it's the encryption of X using QFHE. And so quantum FHE works in the following way. So in order to evaluate an encryption of X on a circuit C, you will get two parts, so quantum part on the left and a classical part on the right. And the quantum part will be this QOTP C of X. So C of X, because C is a quantum circuit, will be a quantum state. And QOTP is quantum one-time pad, is just masking this quantum state with a key SS prime. And the classical part will be the encryption of this SS prime. So now how this preparation protocol works. So we have a sender and a receiver. The sender will send an encryption of a subspace description A to the receiver. Then the receiver will evaluate this encryption on a circuit C, such that C on A outputs the superposition over all the vectors in the subspace A. And this is called a subspace state. And what this receiver will get out of this evaluation protocol is actually the quantum one-time pad masking of this subspace state, which is actually exactly a coset state. So it will get this coset state A SS prime. It will also get the encryption of the key S and S prime that he can send back to the sender. And the sender, because he has the key, will be able to decrypt everything, get the description of the coset state, while the receiver has the coset state. But the problem of this protocol is that in our case, in our monogamy of entanglement setting, there is a simple attack, a simple cloning attack, and mainly it's due to the fact that we do not check whether the receiver really compute the right circuit during the evaluation phase. And so the solution is to use, as I said, a self-testing protocol with this combined with this quantum fully homomorphic encryption-based coset state preparation protocol. And so we will use a self-testing protocol of BB84 states presented by GMP22. And so this self-testing protocol works in the following way. So we have a verifier interacting with the prover, and the idea is that the prover will first prepare some plus states, then commit to the plus state using some kind of Mahadev commitment for those who know what it is. Then they will continue to interact, and what is important here is that right before the final message from the prover to the verifier, we know that first the verifier will know some theta v, which is a description of a BB84 state, and the prover has in its memory the corresponding BB84 states. And that is true even for a malicious prover. That is true even for a malicious prover if the verifier accepts in the end of the protocol. So we will just make a couple of observations here on how we can modify this protocol. So the first one is that we can change the way the prover prepares these plus states. And this is done by the verifier sending an encryption of 0 to the prover, and the prover evaluating this encryption of a circuit C, which on 0 outputs these plus states. So actually what we will get is not exactly these plus states, because it will be masked by the quantum one-time pad, but it will be close enough, and it's sufficient to show that with this new preparation, we can have the same correctness and the same soundness. So this protocol is exactly the same in terms of correctness and soundness than the previous one. And because we use quantum FHE, we can combine it. We can actually change the encryption. And instead of sending the encryption of 0, we can send the encryption of A. And the prover will evaluate on the same circuit as we saw before. And so it will get a coset state. And by changing some things, by doing some little change on the verifier part, we can show that this actually, the verifier will get the description of the coset, and the prover will get the coset in the end. And it will be completely indistinguishable from the previous protocol where we sent the encryption of 0. And because of this fact, we can combine these two protocols, so send a bunch of encryption of 0 at the beginning, then once we are sure that the prover is honest, send a round with the encryption of A, and it gives us actually in the end a self-testing protocol for the cosset state. Okay, so I will skip the last part, but basically we just have to run this protocol. Once you have the self-testing, we just have to run it in a n among 2n cut and choose way to get the remote cosset state preparation. And yeah, thank you for your attention.
Questions? Have a couple of questions. So one is that in GMP, they have this inverse polynomial error.
Yeah.
And do you incur that error or?
Yeah, actually, so we have this error in the end. So the state that the prover gets in the end is cosset state up to some polynomial error. The thing is that we don't need to check exactly that we don't need this prover to have this cosset state exactly. We only need to say that if he doesn't have this cosset states, as long as he cannot win the monogamy entanglement, it's fine, and that we can show it with negligible.
Okay, I guess what you're saying is that you don't need that strong rigidity statement that they have.
We don't need a perfect soundness to get our security.
One other quick question. So you talked about like replacing encryption of 0 with encryption of A. I mean, I guess Alice cannot distinguish this, but later on, Bob and Charlie do receive A, right? Can't they actually distinguish?
Yeah, I see your points. But I guess so they can't distinguish, otherwise they could break the security. Yeah. So I don't remember how we got rid of this this problem, and we show that it's not a problem anymore.
Okay. Right. Let's thank the speaker again. The next talk is about pseudorandom states with interesting properties and their cryptographic applications. It's by Amit Pera is going to give the talk.
Hi, can you hear me? All right. So thanks for having me. So today I'm going to talk about pseudorandom quantum states, proof of destruction. It's a joint work with Zvika Vekutsky, Om Dishmaeli, and Oshatat. Okay, let's get started. So I'd like to start with the first part of the title, which is pseudorandom quantum states. We have already seen a few presentations discussing this. So let's recall what it is. So it's basically, again, like an efficient quantum algorithm, generator gen, along with a key space or the seed space, such that this algorithm gen, for every key in the key space, outputs a pure state psi k, a quantum state psi k. And the pseudo-randomness basically says that for any efficient adversary and any polynomial t, the following two scenarios are indistinguishable. In the first scenario, the challenger samples a key from the uniformly at random and gives few copies of psi k. And in the other case, the challenger samples just a hard random state. So hard random is like the analogous of uniformly random string in the classical setting. So in the quantum setting, we say like it's a continuous space, so it's a hard measure. So uniformly hard random state phi, and gives q copies of phi to the adversary. And by indistinguishability, you again mean the usual indistinguishability, that is the probability that the adversary outputs 1 is close in both the setting, negligibly close. All right. So as you can see, this is just like a PRG, but with the only difference that we give many copies of the output state instead of 1. This is because in the quantum setting, you cannot get many copies of the output state, output quantum state from one copy, because cloning is not allowed, and in fact, in pseudorandom states, it's computationally hard to clone. Okay, so now that we saw like an analog of PRG, the natural next step would be to see an analog of PRF. So this is what we call pseudorandom function-like states, or PRFS. So we have two acronyms now: PRS for pseudorandom states and PRFS for pseudorandom function-like states. So now we have an input space along with the key space and the generator algorithm, and so it's again the generation algorithm takes a key and an input x and outputs a pure state. And again, the pseudo randomness condition we can view as the following, again an indistinguishability game. But now in the first case, the adversary receives the following. So the challenger samples a key at random and gives oracle access to the gen with the key k hard coded in it. In the other setting, the adversary gets access to the hard oracle, where the hard oracle basically samples a hard random state mu x for every input x, and every time the adversary asks for queries x, it just outputs mu x. And again, the same indistinguishability as we saw in the previous slide. Okay, now let me go to the next part of the title, which was quantum states with proof of destruction. So I would like to illustrate this with the following example of quantum money. So imagine you have a bank which has some secret classical information k, and using which it mints money states sigma. And now a user, a customer, Bob, comes up and says, look, I have some money and I want to deposit it to an account. It could be his own account or somebody else's account, but he wants to deposit. So how can he accomplish this task? One way is to just send this quantum state over a quantum channel, and then the bank can just verify, and if the verify using the secret key, and then if the verification passes, then the bank can top up the account. But in this way, the problem is that this quantum channel with which Bob sends the state could have noise, and they can be notoriously hard to deal with. So is there like a easier way to do this just by, let's say, sending classical bits? So this is where proof of destruction come in. So what Bob can do is that he can measure the state in some basis that is prescribed by the bank publicly. And this measurement is destructive in some sense. So it will destroy the state Bob possesses, and instead output this classical proof P, and then send this proof P to bank. So Bob sends the proof P to the bank, and the bank has a secret key using which the bank can verify. And if the verification passes, then the bank is assured that indeed Bob had this money state and he destroyed it now, so he can so the bank will deposit the money. Okay. Now that we have seen both these notions, let's see some of the previous works that tries to accomplish this. So there has been a lot of work that uses these co-state states that we just saw in the previous talk to achieve many cryptographic primitives that exploit this proof of destruction property. And so all of these constructions achieve proof of destruction, but these states, co-state states, have too much structure. So you can easily distinguish it from random. Hence, these are not pseudo-random. On the other hand, we have these constructions of pseudo-random states based on these random phases. So they do achieve pseudo-randomness by design, but unfortunately, for these constructions, we don't know like how can we achieve proof of destruction. Essentially, because of the same reason, that we don't have enough structure there to work with. So in this work, we managed to kind of meet in the middle, and by modifying this random phase state construction and achieve both pseudo-randomness and proof of destruction. Okay, now let's see formally how to combine these two notions. So let's look into the definitions. So this combined idea we call pseudo-random states with proof of destruction. So now it becomes PRSPD. My apologies for the long name. Okay, so what's the definition? So we have a key space again, and now, but we have a triplet of efficient algorithms, not just one. So the first one is again the generation algorithm that takes a seed k and outputs psi k. But now we also have the destruction algorithm that takes a quantum state and outputs a classical string. So you can think of it like a measurement. And then we have the verification algorithm that uses the secret key to verify the authenticity of an alleged proof P. And correctness basically said that if you have like if you generated a state using the gen algorithm using a key k and then use destruct on it, then the resulting proof will pass verification with respect to the key. So I hope the notion is clear. So okay, now let's look into the security of this definition. So first is pseudo-randomness. So again, for this part, you can just for pseudo-randomness, you can think of the PRS PD family as just a PRS family, like a pseudo-random state family, and then demand pseudo-randomness. So that is exactly the same here. Next is unforgeability of proof, which was not there in pseudo-random states, and this can be explained in the following unforgeability game. So the adversary has access to the verification oracle. So think that the challenger sampled a key k and gave oracle access to the verification with respect to key k, and also gave t copies of the state psi k. Now this t is some polynomial that the adversary can choose, and then the adversary wins if he manages to produce t plus 1 distinct proofs that pass verification. And we say that the scheme achieves unforgeability of proofs if there is no QPT adversary that can do this except with negligible probability. All right. So now let's look into a construction. So as hinted earlier, a construction is based on modifying the random phase state construction for pseudo-random states. So it's a good idea to let's recall the PRS construction there. So this construction uses pseudo-random function family or PRF, and the key space of the PRS family is the same as the key space of the PRF family, and the states basically look like this. For every key k, the psi k is basically a uniform superposition, but with this random phase determine this function fk. Okay. What we managed to do is that look, the previous the construction there has the problem that the superposition is over the whole, like all the strings, and therefore we don't know how can we do proof of destruction because there is not enough structure. So what we do is that we sparsify the construction. So we have the same construction, but instead of taking like superposition over all strings, we take superposition over a pseudo-random set of size 2 to the n by 2. Now you should interpret this size 2 to the n by 2 is something which is super polynomial. So it is enough to fool the distinguishing adversary in the pseudo-randomness game, but it is still asymptotically smaller than the whole space, so that you have enough structure to do proof of destruction. So how do we achieve this pseudo-random state is that we use a strong PRP. So our pseudo-random state is basically you take a random permutation from this family and you apply it on this fixed set of size 2 to the n by 2, which is, you can take any set, but we took this set, all set of strings with prefix 0 n by 2. And therefore, the key space now becomes the product of the key space of the PRF and the strong PRP. Just to remark, we need the strong PRP in order to construct the superposition because we also need the inverse access to the inverse permutation. And now the destruct algorithm is simply measuring it in the computational basis, and verification is just checking membership in this set SR, in the pseudo-random set SR. All right. So we so far only talked about PRS-PD or pseudo-random states with proof of destruction, but we can also associate proof of destruction with pseudo-random function. And then it turns out this definition can be naturally generalized, and also our construction can be naturally generalized. So what we actually get is that we can construct both PRS-PD and PRFS-PD from one-way functions. Now let's look into a few of the applications. So it was shown that pseudo-random states and pseudo-random function-like states has a lot of applications in quantum cryptography. So what we managed to show is that with proof of destruction, okay, so all these constructions use quantum communication, like the protocols and the primitives both use quantum communication. So what we managed to do is to get these with classical communication using proof of destruction. Okay, but why is this interesting? Well, it's interesting because as we saw earlier, that there is this separation result between PRS and PRFS from one-way functions. So what it also says is all these applications is also separated from one-way functions. But remember, these applications are with quantum communication. So the question is, can we have a similar separation with classical communication as well? And do we have such a thing? The answer is we don't know yet. because the same separation as that works for pseudo-random states and pseudo-random function-like states do not work for the proof of destruction analogs. And therefore, we still don't know if with classical communication, these protocols are weaker than one-way functions. And therefore, the main open question that remains is, can we show that both PRSPD and PRFSPD are weaker than one-way functions? Okay. And so if you look at the current status of microclave, it looks quite complicated. The point of it is just to show how like it has got complicated, and there are many open directions here that needs to be investigated. And with that, I would like to conclude.
Oh, one question.
So I think if you use log qubit output PRSG, you can also realize some classical channel application. How this is different from?
Yeah, so we don't know so that's true. There's another route to get this classical communication using logarithmic output pseudo-random states and pseudo-random function-like states. So yeah, these two assumptions, we don't know the relation between them yet, like which one is, like it might be the case even that both of them are incomparable, but currently we don't have any evidence to show that one is weaker than the other.
And so PRSG can be broken with PP oracle.
Yeah.
So can you break your primitive with QCMA oracle?
It's not clear, but you might. The reason I'm saying it's not clear is because this proof of destruction, they are not really deterministic from the key. So there might be issues if you want to apply the same argument, but yeah, I don't know. I cannot say you cannot.
Any other questions? Okay, let's thank the speaker again. So the next talk is a soft merge of two talks. The first one will be presented by Giulio Manavolta. The talk is on weakening assumptions for certified deletion.
Hello. One second. Let me figure out how this works first. Okay. Great. So thanks for the introduction. I'm going to talk about weakening assumptions for publicly verifiable deletion. This is a joint work with James, Dakshita, Alex, and Michael. Okay, so let me start off with explaining what we're doing and the scenario that we consider. So we consider a scenario where a client holds some data and they want to outsource it to a server. And at some point, the client says, okay, please delete my data. And the server will send a certificate. At that point, supposedly, the data is gone from the server. Okay. Now, if you consider classical information alone, is not hard to convince yourself that this task is only possible if the server is honest and it sort of tries to cooperate with you. Whereas when taking into account also quantum information, then we can hope to actually achieve this also in a setting where the server is malicious. And that's exactly what we are considering. But maybe a slightly nuanced point is that even using quantum information, we have to always keep in mind that there must be some information about the data which is not known to the server. And one way to enforce that, otherwise it's clearly impossible. So one way to enforce that is to consider a server which is computationally bounded, which is QPT. And this motivates us and other people to look into many cryptographic primitives with certified deletion. So you can define certified deletion for primitives such as commitment, secret key encryption, public key encryption, and so on and so on. And those are all well defined, and you can try to construct them. And that's essentially what we're trying to do in this work. Now, before telling you what our results are, let me show you what's known. This is a very active area of research, and here is an incomplete list of a paper that consider this problem in one setting or another. But one thing that all these works have in common is the fact that the deletion process is privately verifiable, a private verification algorithm, which means that to verify that the data has been effectively deleted, you need some secret information that should not be revealed to the server who is supposedly deleting data. Now, here are a few works that actually consider the problem of public verification for deletion, in the sense that there is no secret information needed to verify the deletion. Here, a work of Bartusek et al. Consider this problem in the context of obfuscation with certified deletion. And a follow-up work by James, Takshira, and Alex show a general compiler for publicly verifiable deletion, which, in addition to the security of the primitive that you are considering, it also requires to assume the existence of almost regular one-way function. It's not maybe super important to know what this object is, but it's somewhat a more structured version of one-way function. And our main result is to directly improve on this work and show a general compiler for certified deletion, assuming just one-way function. So any one-way function, and we also have as an additional result, we also have a generic compiler using a one-way state generators. Although in this setting we obtain a scheme where the key to verify deletion is a quantum state. Okay, and so of course the difference between these two settings is that the assumption of one-way state generators is believed to be a weaker assumption than one-way functions. And I also want to mention the existence of a concurrent work, which you will hear next, where they present a compiler which is very similar, but somewhat interesting is not identical, and also assumes one-way function. And they also have a very, very beautiful argument to show that this compiler is somewhat uses, in a sense, minimal assumptions. And okay, I'm not going to say more because you're going to hear the talk of Takashi next. Good. So without further ado, I will show you our compiler for the simplified setting of one-way functions, and considering just an encryption scheme, which I think is sufficient to convey the intuition. And the compiler is very natural. So the verification key simply consists of two images of a one-way function. And the ciphertext consists of an encryption of x0, x0, x1, along with the following quantum state, which is just a uniform superposition of x0 and x1, which are the preimages of y0 and y1, except that we sort of conditionally flip the phase, depending on whether we want to encrypt 0 or 1. So now you should think of the message here as the bit. It's a very natural compiler. So I have to tell you two things: how to decrypt and how to delete. Okay. So if we have the secret key, decryption is very easy. You can just measure the state in the Hadamard basis, and with the result of the measurement and along with the secret key of the encryption, you can actually recover the message. It's an exercise for you to figure out how to do it. It's very simple. Whereas for deleting, of course, what do we do? Well, we just measure in the conjugate basis. So we measure in the computational basis. And if you look at the state, what you will get, well, you will get just one of the two preimages with equal probability. And at this point, it's obvious how to verify. You can just simply check whether whatever you get is either a preimage of y0 or a preimage of y1. Okay, so very natural. Now the main theory. Oh, sorry. Yes, forgot to say that this actually is a technique which was inspired from recent work of quantum public key, one of which you heard earlier in this session. Good. So the main theorem that we prove here is this one. So we consider two experiments. The experiments are identical in the sense that we just give the adversary all the information that we said before. The adversary returns a string x0, which is either a preimage of y0 or y1. And the only difference is the phase of the state. So the relative phase of the state, which again models precisely having an encryption of 0 or an encryption of 1. And in this context, we want that if we consider the joint distribution of the state of the adversary, the trace distance between these two experiments is negligible in lambda, and lambda is a security parameter. And for those of you who don't know what the trace distance is, that's essentially the sort of quantum analog of the L1 norm that we normally consider for distance between probability distributions. Good. So it's a statistical property. Maybe that's the important part. Now, I claim that the proof is not as obvious as you might think. For instance, like a natural way to prove that these two distributions are indistinguishable would be to sort of switch the encryption to be an encryption, let's say, of 0. But that doesn't work precisely because the property that we want to show is a statistical property. So you're not allowed to, to change a distribution in a computational way, but not in a statistical way. So that change is computationally indistinguishable, but statistically detectable. So would not be allowed. So we have to use a different strategy, which I'm going to outline next. So the first step of the proof is somewhat standard in this setting, which consists of sort of delaying the choice of the bit. So we sort of entangle the phase of the quantum state as you saw it before with an extra register that we keep locally, which contains a uniform superposition of 0 and 1. And in the second step, we instead of just measuring the register in the computational basis, we first measure it in the Hadamard basis and then measure it in the computational basis. And at this point, it's sort of obvious that the success probability of the experiment will be exactly 1/2, because we're guaranteed that the register, after we measure it in the Hadamard basis, is exactly, it's exactly at 45 degrees with the computational basis. So the probability that we'll get 0 or 1 is exactly 1/2. Okay. So the way in which we actually use the property of the encryption scheme is by arguing that the view induced by the step 1 and step 2, they are computationally indistinguishable. So it's a little subtle, but somehow we have to use the fact that we have to be able to use the property of the encryption just to argue that these two experiments are computationally indistinguishable. So we use it in a somewhat indirect way, but it works. Good. Okay, so with that being said, I'll wrap up and I'll give the stage to Takashi. So let me just quickly summarize. We presented a general compiler for certified deletion for X being your favorite cryptographic primitive, commitments, PKE, ABE, FHE, and so on, assuming either one-way function or one-way state generators. And let me tell just very few open problems. An very interesting open problem is just to make this construction, for instance, practical, like that you can build using quantum hardware that we have today. For instance, you would be able to do it if you can construct this scheme using what I call product states, so like qubit by qubit states, which is not the case for our construction. For instance, like BB84 states are good states that we can prepare. Another interesting question is really if you can do it even from weaker assumptions, placing maybe a little bit more constraints on the setup, for instance, allowing quantum states for verification key. So it's in that case, it's not clear that this is an optimal approach. And of course, a very interesting open-ended question is whether you can do more cryptography with certified deletion. And part of the research question is to figure out what that even means. And okay, yeah. With that being said, I'll leave the stage to Takashi. Thank you.
Any quick questions to Giulio? So you mentioned that the trace distance between out 0 and out 1 was negligible. Unless I misunderstood, aren't you considering orthogonal states? Isn't x0 plus x1 orthogonal to x0 minus x1? So how can the trace distance be negligible there?
Sorry, let me go back.
Yeah,
so you mean, okay, good. No, okay. So let me be more precise what I mean. So I mean that if I consider an experiment after the adversary has output some x star such that is either a preimage of x0 or x1, like the residual state.
Oh, I see.
Okay. In the sense, like this essentially means if the adversary was honest, it would have measured that state in the computational basis, so any information in the phase would have been erased.
Yeah, thanks.
More quick questions?
Okay, thanks. The next talk is by Takashi Yamakawa on publicly verifiable deletion from minimal assumptions.
Thank you for the introduction. So I will talk about this work. So this is our result. We construct a generic compiler that has the publicly verifiable deletion property for various kinds of encryption schemes, only using one functions. And as Jerry mentioned, this conclusion is almost the same as their work, the previous talk, except for some minor difference. But I would like to mention that the constructions are not identical, and the idea is quite different. And our main idea is to generate signatures for BBH for states. And this idea is inspired by a recent work on FE function encryption with certified deletion, which is our another work. And we also give some additional observation that the assumption can be weakened to a minimum one. And I remarked that one function may not be a minimal assumption in quantum crypto. And we observed that the one functions in our construction can be replaced with what we call hard quantum planted problems for NP, which I will explain later. And because Jerry already gave background, so I will directly go into the technique. So before explaining our idea, let me first introduce the previous compiler for privately verifiable deletion by Bartek and Grana. So this is notation. So for L-bit string x and theta, x sub theta means the BB84 state corresponding to x and theta. And ENC is an encryption algorithm of some encryption scheme that may not support certified deletion. And for encrypting a one-bit message MSG, the encryptor first uniformly samples L-bit strings x and theta, and the ciphertext is described like this. The first component of the ciphertext is encryption of the basic choice theta, and the message masked by the XOR of OR XJ corresponding to the Hadamard-based position. And the second component of the ciphertext is the BB84 state corresponding to x and theta. And for decryption, if one is given the decryption key for ENC, one can first recover the base choice theta, and then by using the BB84 state, you can recover X, and finally you can unmask the message. I mean the mask part of the message to recover the message. And for deletion, the receiver measures the BB84 state in the standard basis, and simply sends the measurement outcome as a deletion certificate. Then the verifier checks if this deletion certificate is consistent to the original X on or the J in the standard basis positions. And intuitively, for passing this verification, the receiver has to measure the BB84 state in the standard basis. But after such a measurement, all information about X in the Hadamard basis position disappear. And after that, the other battery, I mean, the receiver cannot recover the message, even if it is given the decryption key. And so this is a nice compiler, but the caveat of this construction is that it is only privately verifiable. Why? This is because the verifier has to know X and theta for checking this. But X and theta should be kept from the other battery, kept secret from the other battery, and this is only privately verifiable. So our idea is to generate a signature for X theta, I mean BB84 state, so that the verification can be done by a public verification of the signature. And but signing on the quantum state is in general known to be impossible. But our key observation is that in their compiler, the verifier only needs to verify the consistency in the standard basis positions. So we can simply run a signing algorithm of some signature scheme in superposition like this. So basically, for state 0, we generate state 0, sigma 0, and 1 post 1. This is mapped to 1, sigma 1, where sigma 0 and sigma 1 are signatures for messages 0 and 1, respectively. And for Hadamard-based states, we simply do like this. And for Hadamard-based states, this signature doesn't ensure anything about the state, but for standard-based bits, this does certify the bit. and this is enough for our construction. And as notation, we write use fig k to mean the operator that applies this map for each qubit by using the signing key fig k. And then our construction is described like this. So this is very similar to the BK construction, except for the following differences. The first, we also encrypt the signing key by using ENC. And the second, we apply this operation using K to the BB8 state. And for deletion, similar to the BK construction, we simply measure this state in the standard basis and send the measurement outcome as a deletion certificate. And the measurement outcome now looks like this, so the pair of the bit and its corresponding signature. And the verifier now only checks that the all message signature pairs are valid. And I remark that this is publicly verifiable because the signatures can be publicly verifiable. And also, we can reduce the certified deletion security of this construction to that of the original BK construction because, as I already explained, the signature certifies the bits on all standard basis positions, and so we can simply reduce. By using this, we can there is a straightforward reduction to the original one. And next, I will explain what signature schemes to use to instantiate our construction. And in our construction, we only generate one signature per signing key, and so we can simply use one-time signature. In particular, we can use Lamport signature based on any volume function like this. And moreover, we observe that we can actually use something weaker assumption, which we call hard content planted problem of NP. What is this? So this is specified by some quantum polytime sampler that samples the instance witness pair XW in such a way that any QPT at about 3 given only instance cannot find its witness. Then we can think of the instance and witness of this as a output and input of the boundary function, and by using the similar construction to Lamport signature, or we can construct similar one-time signature scheme. And we can use this signature scheme to instantiate our construction. And we also observe that this is the minimum assumption as long as the verification is classical. Why? This is because any publicly verifiable deletion encryption scheme with classical verification naturally implies this because the verification of the certificate can be seen as a NP verification algorithm. So this is the minimum assumption in this sense. And this is a summary. Thank you for your attention.
Any questions for Takashi? Yeah.
So how does this assumption about the planted NP relate to other cryptographic primitives in microcrypt like EFI and let's say one vested generators? Because you said it's equivalent to this public verification, right?
So I don't know any other relationship between this assumption. I mean, for example, it's easy to see that this is, of course, weaker than the existing boundary function. And we can also say that the publicly verifiable deletion with the classical verification implies this. And so by minimum assumption, I mean for constructing this, we have to at least assume this. And this is why I said this is minimum assumption. But for the relationship between something else like the one-way SG or AFI, I have no idea. But I guess it's unlikely that there is any relationship.
Because this assumption of hard quantum planted problem for NP, won't it be broken by strong enough oracles? I think EFI is usually resistant to such attacks.
Yes, I mean, so far we don't know how to break EFI by using any classical oracle, but I guess for this we can break. So in that case, this cannot be reduced to EFI, and we can believe so. But there is no rigorous proof that EFI cannot be reduced to classical complexity. So I don't know. So if we can formally prove that.
Thanks.
I have a question. So you said that this is a minimal assumption. So I can think of the certificate that you send back to be the witness, but what would be the instance here?
The instance is okay. So I haven't defined the syntax of the publicly verified validation, but there is a verification key, and the verification key.
Oh, there's the
yeah,
instance. I see. Any other questions? Okay, so let's thank all the speakers. Let's thank Takashi and also all the speakers of the session. Please don't go anywhere. Tal Malkin has a very, very important announcement. I can oversell, it's fine.
Hello? Yeah. Good. This is the Theory of Cryptography conference. So I wanted, no, start with the other one. You can. I wanted to advertise two journals, one for theory and one for cryptography, for you to submit your papers to. So it's like a commercial break very quickly. They're both new, that's why I'm advertising them. This is a theory journal, Theoretics, new journal that's just started. Good. This is, I'm gonna really very quickly go through the slides. I just wanted to advertise the point. This is an ad for why open access is super important. I think we all agree that it's super important. Theoretics is a new open access journal for all areas of theoretical computer science. The advisory board has representatives from all major theory conferences. I'm the TCC representative. Very strong editorial board. The editors-in-chief is Uri Tzvik and Javier Esparza. And we aim to be, I'm in the advisory board, not part of the actual journal. The target level is to be super high quality on the like SciComp and JACM. Started really recently in 2019, and so far 11 articles were accepted. You should submit your work. That's basically it. Okay, the idea is it will be very fast. Okay, so stage one is very quickly you get a decision, like a one-bit decision super quickly, and then the second stage is more about really verifying correctness of everything. Yeah, that's all for this one. Don't go. Can I start the other one? That's a theory journal. Next, I'll tell you quickly about a crypto journal. Yeah, ISCR Communications and Cryptology. Thank you. So this is slightly older, but still super new. A new journal of cryptology. Okay, these are the editors-in-chief, Joppe Boss and Andreas Holsing. And these are area chairs. I think the one most relevant to TCC is Kaimin. Okay, maybe I should have put them first, but these slides, I didn't make them. I just inherited them. Okay, and these are the principles. I won't go through it in detail, but it was also presented in some other conferences, like crypto. But it's also open access, which is super important, low cost, also meant to be fast and consistent turnaround time. And it's very broad in terms of the publication slots. Okay, and good. Promote positive review culture and no travel. The red line was supposed to be around TCC. It's the scope of the journal is really everything related to cryptography. And yeah, it's about to start. The first deadline is January 8th. And okay, this is thanks to Kevin. There's a lot of stuff. I wanted this one. Yeah, conclusions. Do you want to not travel to publish, then submit your work to this journal. Good. And if you don't want to get another reviewer to review. So actually, TCC is exactly in the intersection of these two journals. So I would encourage you to submit to them. Okay, thank you. That's it for the announcement. Now you can go to lunch, I guess.
Excuse me for a moment. So a couple of announcements. And so today, this is the last day, and we would appreciate if people can clear out of this building by 5 o'clock. And at 5 o'clock, there's also buses going back to Nangang Station for those that needs it. Also, we are looking for a few people. Yu Xia, Rex Fernando, Walter McKelvey, Yanbo Chen, and Yaoting Lin. Could you find this Miss Seya Pan at the registration desk, please? We are out of conference kits, and there is a couple of small T-shirts. Thank you. And lunch. Hello.
All right, let's get started. Welcome to the group-based crypto session. And we have 4 talks in this session. So we'll start off by hearing about how to build verifiable delay functions from Luca sequences. The work is by Charlotte Hoffman, Pavel Kubacek, Chetan Kamath, Tomasz Kerniak, and Tomasz will give the talk.
Hello, everybody. In this speech, I will introduce verifiable delay functions and Luca sequences, and then we will put it together and we will discuss sequentiality and verifiability of our VDF candidate. So verifiable delay function is a function parameterized by some t, and we require it to have two properties. First of them is sequentiality, which means that evaluation of ft requires t sequential steps. And this computation cannot be speeded up even when some parallelism is available. And usually we reach this property by taking some atomic function, f. You can think about f like it can be a hash function, and we compose it f times, t times. And the second property is public verifiability, which means that there exists an efficient algorithm P such that P on input X and T evaluates the function, and at the same time, it produces a proof pi for a relation ftx equals y. Verifiable delay functions have many applications. We can build resource-efficient blockchains from them, random beacons, short-lived crypto primitives, proof of data replications, and many others. Despite the fact we have so many applications, there are not so many practical constructions. The most practical ones are from Piecak and Veselovsky, and they are based on hidden order groups like RSA group or a class group of quadratic residues. And we have other candidates based on snarks. We have some based on isogenies, some candidates based on squaring in finite fields. And very recently, we have some first quantum resistant candidates based on lattices from Malavota et al. So we were searching for another source of sequentiality, and we come up with this idea of taking Luca sequences as a base for the construction. So what Luca sequences are, we have two of them. It's a sequence U and V, parameterized by some Q and P. And these are linear recurrent sequences of order 2. They are generalization of many other well-known integer sequences like Fibonacci numbers or Pell numbers. And they have found many applications in number theory, namely we have some primality tests and factorization algorithms based on them. And also there were some attempts to build crypto systems based on Luca sequences, but these were not shown to have any significant advantages over the state-of-the-art solution. So how to put it together? Our construction is pretty straightforward. Function gt takes parameters p and q, and it produces 2 to the thief members of the sequence u and sequence v. It's a well-known effect that we have closed formulae for recurrent linear sequences. In this case, we are taking roots of the characteristic polynomial of a sequence, and we are able to express nth member of sequence u and v by nth power of these two roots. It's a root and its complement. And I want to emphasize on this place that these roots, they belong to some extension field, namely we extend group Zn by square root of discriminant of the characteristic polynomial. And this simplifies our notion extremely, and it also simplifies reasoning about our PDF. So let's discuss the sequentiality. Here, I would like to refer to the delay function which was introduced by Rivest Shamir Wagner in 1906. You cannot really prove sequentiality. You have to introduce some hardness assumption, and that's exactly what they did in their paper. They stated that this iterated modular squaring is sequential, and they do it implicitly in the paper. we would like to get a similar claim for our VDF. And here we have a positive result of our work because we are able to reduce sequentiality of Lucas verifiable delay function to the sequentiality of RSW function. And I would like to show you the reduction now because it's not that difficult. So we have some identity for Lucas sequences, which allows us to compute 2 to the t power of the parameter q whenever we have computed 2 to the t members of Lucas sequences u and v. We can use it for the reduction in this way. So we are given some algorithm which computes Lucas sequences, and we are given some x. We set q to be equal to x, and we pick a random p. We compute Lucas sequences u and v. We plug in the result into the identity, and in the end, we will get appropriate power of x. And naturally, we have tried to do reduction in the other way, and we haven't found any. And we have some evidence why this is not possible. Namely, for example, we use RSA group only. We don't use only multiplicative group of RSA, but we use full arithmetic of the RSA ring. And we have conjectured that there probably will be some sequentiality gap between RSW function and the delay function based on Lucas sequences, which is good news because if this is true, then, for example, if a new algorithm for computing modular iterated squaring in RSA group will emerge in the future, it will not necessarily affect security of our construction. And finally, let's discuss the verifiability. Here we adapted Pietasachs protocol, which is a folding protocol. It works in a way that in the beginning we are given some instance x maps to y in t sequential steps. And we take some midpoint of this function, midpoint mu, to split this instance into 2 instances of half size. And then the verifier picks some randomness, and we merge these 2 half size instances into 1 half size instance. This goes on and on until we finally, after log t steps, reach instance of size 1, which is easily verifiable by squaring x and comparing with y. Let me sum up which modifications we had to do, comparing Pietasachs' work with our work. So we use a different base group. We use the same function, but over a different group. And we had to be real careful about choice of the factors of our moduli, because for the soundness of the protocol, we need to avoid all groups of small order or all subgroups of small order. And in Pietzak case, this is easily doable by choosing safe primes. In our case, we need to satisfy additional condition, and that is that also ZP plus 1 taken as multiplicative group doesn't have any subgroups of small order. And we have shown in the work some algorithms how to sample these strong primes. We have also tested this, like really generating some examples of them. And the only problem with strong primes is that there always must be some cofactor by the construction. So in Pietzak case, there is a cofactor 2. In our case, there will be some small constant a as a cofactor which has to be cleared before we get a group without subgroups of small order. And this causes another trouble, namely we need group membership verifiability, which is quite easy in Pietzak case, because in Pietzak case, for verifiability, it's enough to take a square root of the element which is sent by prover, and the square root is easily obtained as a previous member of a sequence, while in our case, we need a root of a midpoint, which is not easily computable in RSA group, but we came with some trick how to do this by delaying cofactor clearing. So let me sum it up and mention some open problems. We have proposed a new VDF candidate based on new hardness assumption. And we have proven that this hardness assumption is actually reducible to the well-known hardness assumption. And also, we have described some generalization of the PSX protocol. And we have stated this conjecture about sequentiality gap between the delay function given by Rivest-Chelmy-Wagner and a delay function based on Luca sequences. And the very important, very interesting open problem I would like to mention in the end of this talk is that actually we were, in the beginning of this work, very interested into different type of moduli. We were interested into Mersenne number moduli, because if we were able to get verifiability for Mersenne prime moduli, then we were able to certify primality or, like, at the end, non-primality of Mersenne numbers. These Mersenne numbers are the biggest prime the humankind knows. You can see an example in the slide. And there is a whole community who are trying to compute them, and it would be very helpful if they had some verifiability, something like more straightforward than just cross-checking computation, which was done by somebody else. And here my colleagues have the first small steps toward this goal, and that's certification of prof numbers, prof and prof primes. Or in their case, they are able to certificate non-primality of these. You can see an example of prof prime in the slide. That's all I wanted to tell you. Thank you for your attention. I open the space for questions.
Any questions? I have a quick one. So are you able to adapt your constructions to have other like VDF properties like uniqueness or tightness?
I don't see straightforward approach how to get uniqueness because of this cofactor clearing, which is different. And I don't know what the tightness is.
Oh, tightness is where if you're given the proof, you're not able to compute the VDF any faster.
Oh, I'm not sure about it.
Okay. Yeah.
Right now.
Thank you. Let's thank the speakers again.
Thank you.
All right. Next up, we'll be hearing about limits in the improvable security of ECDSA signatures by Dominique Hartmann and Aika Kiltz, and Dominique will give the talk.
Okay, thanks for the introduction. Yeah, I'm going to talk about the limits in the provable security of ECDSA signatures. This is joint work with my advisor, Eike Kills. And so, first of all, why would we even still bother with ECDSA signatures? Well, mostly because they are just ubiquitous. You see them in TLS, in blockchains, in JSON Web Tokens, basically everywhere. However, despite the ubiquity, there are still comparatively few security results on them. And all of them require some very strong idealizations like random oracles or similar. So this is often a very uncomfortable situation, and we would like to have standard model results. So let's look at ECDSA and see why this is necessary. Or rather, we won't look at ECDSA specifically, but at GenDSA, which is a generalization, where we just say we use a group and not a specific one, which makes our results a bit more general. So key generation is very simple. We sample an exponent. This is our secret key, and G to this secret key to our secret key is our verification key. And to sign a message, we first start with basically the same. We again sample a random group element, big R, and we hash our message. And now comes in the weird part of ECDSA. It's this conversion function f, which takes a group element and maps it to an exponent. However, this has nothing to do with the discrete logarithm, and I'll get more into details on this later. For now, just believe me, you can efficiently compute this function f, and it is important. As a last part, we compute this value s, which basically combines all the previous values we computed. And if t and s are non-zero, then they form our signature, otherwise we'll have to try again. Verification also checks that t and s are non-zero, and we recompute the hash and check this complicated looking equation, which basically just recomputes the big R from signing and checks that f of this recomputed value is actually the same as the t we received as a signature. So let's look more at this conversion function. It was pointed out rather early that this is very important to the security of ECDSA. However, in practice, this function is very simple. Namely, for DSA, where our group is just a prime order subgroup of a finite field, we just take the group element, look at the bit representation, see this as an integer, and reduce it modulo p, and that's the output. And for ECDSA, it's not more complicated. We take the x-coordinate of our curve point and again reduce its bit representation as an integer modulo p. So the upside of this function is that it completely breaks algebraic meaning, because like this resulting number has nothing to do with the group element, except that it basically shares almost the complete bit representation, but it has no connection to like its discrete logarithm or anything. However, on the other hand, it has nothing like unpredictability, which I don't define. It's just, it is not random at all. You don't introduce any randomness. It's not like a hash function that is supposed to look random. It's basically just we throw away some bits by reducing modulo p, and that's it. So where's the problem? Well, the problem is, it was shown rather early that it is unlikely that we can find a standard model proof for ECDSA, or GenDSA, so we have to idealize. And there are three parts which we could look at. And the first one is, of course, the hash function, which we could model as a random oracle. This was done by Fershad in 2017, but they don't get full security. So that's unfortunate. And actually, it turns out in this work that their limitation is inherent. So we could also idealize the group as a generic group, which was done by Groth and Schub. But this is an even stronger idealization than the random oracle model, so we would also like to avoid this. So what we look at is the conversion function, which also by Fershad in the different paper was idealized as a so-called programmable bijective random oracle, which is basically a random bijection. And we will look more into this. And for that, let's look at how they actually model this conversion function. Namely, they don't model the complete function as an idealized object, but they split it into three smaller functions. Namely, this phi, pi, and psi. And they all have one part to play in this reduction or in this structure that I told you about. Namely, if we again look at the example of ECDSA, this psi in the beginning maps a curve point to its x-coordinate, or rather the bit representation. The pi in the middle performs this reinterpretation as an integer, and the psi is the reduction modulo p. So we have these three components, and we only idealize the one in the middle. And we now model this as a bijective random oracle, so as a random bijection where everyone has oracle access to a forward and backwards oracle. However, I just told you that this pi in the middle basically just reinterprets a bit string as a number. So basically, it doesn't really do anything. It doesn't change bit representation. But now in the proof, we suddenly have to model this as a perfectly random function. This is somewhat unrealistic. And so we asked ourselves the question, is it necessary? Or can we do with something weaker, which is hopefully more realistic? And for that, we looked at the previous results by Fershad al, which show that from the discrete logarithm assumption, we get U of NMA security if we model F as a programmable bijective random oracle and also use rewinding. And we also get full U of CMA security from NMA security, again, if we allow F to be a programmable bijective random oracle in the sense that I showed you before. We contrast this with impossibility results, namely we show if we remove even one of these properties, then suddenly we can't get a proof anymore. And as an additional result, we also show that the generic loss of a linear loss in the number of users for multi-user security, showed by Galbraith et al., is also apparently inherent for ECDSA. So let me give you an intuition on how we arrive at these results. And for that, first, let's talk about how we get security in the first place. Usually, we do this by a reduction. And for such a reduction, we assume that there exists an adversary and show if we have such an adversary, we can build a reduction that breaks some hard problem. But now we want to show that there can't be a reduction, so we just treat the reduction as our adversary, and we do this in a so-called meta-reduction. So now we assume that we have this reduction in the middle, which simulates everything it has to do for an assumed adversary. And but now we assume that this reduction exists. So we, as the meta-reduction, now want to use it in the same way we usually use an adversary as a reduction to break some hard problem P prime. So in order to do this, we now have to simulate an adversary as well as the problem that R is supposed to break. And notice here that this oracle O that the reduction simulates for the adversary is internal to the reduction because it's a programmable oracle. The reduction has full control over it and can just do with it whatever it wants. On the other hand, if we look at this oracle as a non-programmable oracle, then it is external to the reduction, so the meta-reduction has to simulate it, which can actually be quite helpful in our proofs. Now, the problem is we now have to simulate an adversary against ECDSA, for which we don't, it's not broken or anything, at least not as far as we know. So we have to simulate such an adversary that is successful, but we don't have the secret key because the reduction just gives us a public key and we have to work with it somehow. So how can we get around this? We do this by using an assumption that the meta-reduction attacks. Namely, we reduce our meta-reduction will break the so-called freebase one more discrete logarithm assumption, which is a slight variant of the maybe more well-known one more discrete logarithm assumption, where in addition to a discrete logarithm challenge, our meta-reduction gets two oracles, namely a discrete logarithm oracle and a challenge oracle. The discrete logarithm oracle basically breaks the discrete logarithm assumption for us, but we can only use it if we query more challenges. So for each additional discrete logarithm challenge that we have to break, we get one query to this oracle. But this oracle is very convenient because it essentially breaks ECDSA for us immediately. But now we have a second problem. We want to use it, so we need more challenges. So how can we extract the solution to all these new challenges that we will need for our simulation? Well, for that, we have to introduce the algebraic group model. So in the end, we show that there can be no algebraic reduction that actually breaks, reduces the security of ECDSA. And also, we use some clever simulation of the non-programmable bijective random oracle, because now in our case, since we in many of our examples assume that it is non-programmable, it is external to the reduction, so our meta-reduction now has full control over it. So maybe let me conclude with some interpretation. Maybe the important question is ECDSA now broken? No, it is not. But we've shown that the proofs require some very strong and potentially unrealistic idealizations, since this modeling of this conversion function using a programmable bijective random oracle is somewhat questionable. Secondly, we use this weird freebase one more discrete logarithm assumption, and this sounds very strong. And often we want to avoid strong assumptions. And of course, this is true here as well, but we only use it for meta reduction. So even if it were to turn out false, then at least we don't lose security and suddenly our data is breached. We only lose the impossibility result, which is unfortunate, but also doesn't hurt anyone. In a sense, it's a win-win situation. Either we break some assumption, or we know lots of information about ECDSA. Finally, can we get around our impossibility results? Yes, in some sense we can, because as I said, we only rule out non-algebraic algebraic reductions and black box reductions. So if someone comes up with a non-algebraic or non-black box reduction, that can get around it. And also we only show that we can't get security from the discrete logarithm assumption. However, all known reductions that are not in the GGM in the end use DLog, So this is also basically applies to all known reduction that we have. That's it for my part. You can find the full version on ePrint, and I'm glad to take questions.
Thank you. Any questions? I have a quick question. Can you elaborate a little bit on the intuition behind how you do the simulation of the oracles in the second step?
Mostly we just do lazy sampling for the most part. The only part where we actually, in a sense, program the oracle is that when we choose group elements for the inverse queries, we choose them in such a way that we know the discrete logarithms, similar to what the AGM gives us for group elements that the reduction outputs anyway, because in the end we will need that to solve the equations to get all the d-logs for our meta reduction.
I see. Thank you. All right, let's thank the speaker again. And yeah. The next talk is on why round robin is optimal for group action-based protocols. It is by Daniele Cozzo, Emmanuel Giunta, and Emmanuel will give the talk.
Hi. Okay. So thanks for the introduction. So today I'm going to talk about round robin protocol and group actions. So let me first define what are group actions. So a group action is a binary operation between a group and a set that is distributed with respect to the operation in the group and is supposedly hard to invert. We are all familiar with examples of group actions, one being, for instance, the scalar multiplication in prime order groups. Although that is not post-quantum secure, of course, it's a little problem. We study group actions because they are supposed to give rise to post-quantum hard problems. We also have some concrete instantiation, but the issue is that in the general case, where the set has no group structure, they have, of course, less structure, so it's hard to come up with construction in this setting. So the problem I will be focused on today is essentially the following. We have n parties with a secret share S, with a secret S shared among them, and they want to reconstruct the action of this secret applied to some given set element. You can think of this as some kind of like reconstruction in the exponent. And this problem is fundamental for many primitives, including distributed key generation or thresholdizing encryption scheme or signature scheme in the setting of group actions. So as a warm-up, let's first see how easy it is to do this in the group setting. In the group setting, if we have, for instance, an additive secret sharing of S being an integer modulo P or modulo Q, every user can simply exponentiate or take a scalar multiplication of the generator times their own share, broadcast the results. Then you can just take all these group elements, add them together, and you get the result. You get S multiplied by G. So this clearly only requires 2 rounds. It's very efficient. Everybody only perform 1 scalar multiplication. So it's extremely efficient. But it strongly relies on the fact that we have an operation on the group, like we have an addition on the group. So the moment we lose this addition on the group, so we don't have an extra structure anymore, things get more complicated. And in particular, one of the best protocol we know in the setting of group action is just a round robin protocol. That is, the first user exponentiates or applies his own secret to the first set element, get the result, and pass this result to the next user. The next user does the same, exponentiates the set element it received by his own secret and pass this to the next player, and so on. So this protocol, in terms of computational efficiency, is as efficient as the one I presented before, but it requires n rounds of communication, which may not scale as nicely as before. And also present another small issue, that is that only the last user eventually get the result, which means that if the last user decides not to share this result to the others, then we may either have to abort the protocol or have some way to recover from these kind of issues. So I will first focus on the second issue because this was actually solved or at least addressed in a previous paper by Defebvre and Meyer in 2020, where essentially they observed that it's possible to just execute n times a round robin protocol. So each time we have we order using a different order. in such a way that every user is the last one in at least one of those execution. And while this is actually very expensive because we require n squared computation, it is also possible to do things a little bit more in a smarter way, batch some of these execution and eventually get communication complexity to and computation complexity to n log n. So the question we ask essentially are if the round complexity or round robin and this communication complexity are optimal, or if there is something we can do to improve them. And before I state our result, let me first spend a few minutes on the model in which we prove our result. That is the generic action model, which was introduced by Duan Hartmann and Kiltz and other people from Bochum. And essentially, the idea is just generalizing the Shoup group model, essentially the DGM, but in the context of group actions. So in this case, set elements are labeled by a random labeling function, this sigma. And there is no circuit that allows the user to compute the group action, but instead the action is performed by an oracle that simply takes one group element, the representation of one set element, and returns the representation of the action applied to this set element. There is a minor note I need to make that we slightly deviate from their model as we do not include extra oracle for some operations that are possible in the specific context of C-side. We don't in particular include an oracle for quadratic twist, but instead we encode this extra operation in the group and generalize a little bit how can this group be. So we assume that the action is not faithful and the group doesn't need to be commutative. Okay, so that was a minor detail. So now we can finally state the result. So the result is that in the generic action model, that is for essentially adversary that or users that use the action in a black box way, and whenever we have a T out of n secret, secret S, T out of n secret shared among n user, so there is no way to compute the action of S on E in less than T rounds, unless the protocol is insecure. And the second result is essentially that any T-round protocol in which T user computes the output in the second to last step cannot require communication complexity smaller than T log T. So essentially that the previous construction by the Febvre-Meyer is optimal. So of course, some consequence of these results. So the way to interpret this is essentially that there are two ways of building protocols from group actions. So one is essentially using the action as a black box and therefore falling in our impossibility results and using any T-round protocols. And the best one is, of course, the round robin because it's computationally efficient. Or the other way is just not using the action in a black box way and using a circuit that evaluates the action. And this is possible. I mean, whenever we have a circuit, then we can reduce the round complexity by running generic MPC, like linear secret sharing based, or even garbled circuits for constant round complexity. But on the other side, this is very inefficient because this action has the circuit representing this action is significantly complex. So now, having stated the results, I would like to give an overview of like how do we get at least the first result. So what are the techniques we used? And before presenting that, I would like first to show how computation in the generic action model look like. So to do so, we study the following setting. So we suppose we have one user who has one set element. And what he can do is like first, he chooses one group element S. And then he has to compute the action of S applied on E0. So how can he possibly do that? So we assume that this user is making several queries to the oracle that is computing the action. So during its execution is going to see several set elements. And all these set elements, I mean, at this moment appear to be quite random, but in fact, we can define a natural relation among these elements. That is, we can say that one set elements yields the next one. If, for instance, D is used to compute E in this case, and the second one was observed before the first one. So given this relation, observe that, of course, the second condition is imposed to avoid cyclics in the graph. And given the first one, we also observe that any edge in the graph is also, to every edge, we can associate the group element A that was used to compute E from D. And the idea is that what you can show is that in this setting, with this notation, the output must always be connected with the input, essentially. So I cannot come up with the output out of thin air. I must always compute the output, sequentially applying the action to the first element. So this is the idea. So now we can move to the interactive setting. So now we have several parties who wants to compute the action of S applied on E0. And as before, they're gonna use the group action oracle to compute several set elements. And again, as before, we can define some relations among these set elements defined by the action, the way the action is computed. So the idea is that we want to show that for any R round protocol that computes the correct output, there must be some path that goes through exactly R users, or at least at most R users, from E0 to the output. Now, this in general need not to be the case. There can be certain cases in which there are paths that goes through many users, although it's somehow weird, because in the same round, users are not allowed to communicate, of course, by definition of round. But what we show, and that's the important thing, is that it's always possible to find at least one path that goes through at most R users. And this allows us to conclude our first results. And the idea is basically that if we have any T-1 round protocol that securely computes, supposedly secure computes the output, we can find such path, and then we can use the group element used by this user to compute the output. Summing all these elements together eventually allows this T-1 user to recompute the secret, which breaks security. So that's it, and I would like to thank you for the attention.
Thank you. Any questions?
How do you formalize this second condition of the first result that the so I guess it's like either you have many rounds or you use a group action in a non-black box way, but do you specifically have to evaluate a circuit computing the group action?
You're referring to the interpretation, right? Like the slides?
Yes.
Yeah. So the thing is that our result is proven in the sort of shoot group model. So the idea is that if you don't rely at all on the circuits, then you're allowed to rely on the set element representation, but not on the circuit. The moment you rely not necessarily on the circuit as a whole, like you don't need maybe to use garbled circuits, but if you rely in some way on how the circuit is defined, then you cannot compile anymore in the this version of the shoot action, this group action model that we defined.
Yeah, thanks.
Thanks for the question.
So the only way to circumvent the lower bound is if you have a circuit that actually computes the group action. That's the only way there, right?
That's the only way I can envision, at least.
Okay.
Okay. Or at least, I mean, I would say formally it's any way that prevents you to compile the adversary into some other algorithm in the generic action model. Yeah.
I see. Thank you.
Thanks.
Any other questions? All right. Let's thank the speaker. We're quite ahead of schedule, but here's our last talk of the session on algebraic group model with oblivious sampling by Heiger Lipma, Roberto Perisella, Jano Sim, and Roberto will be giving a talk.
Thank you for the introduction. This is a joint work with Helger Lipma and Jano Sim. Okay, we will deal with cryptographic groups. So let me introduce the notation that I use. I will use bracket notation, which means that a group generated by this generator, I indicate the generator with the 1 in bracket, and I indicate a group element with the x in bracket. So particularly the group element of order x with x in bracket. And the group is additive, so the group operation is the addition. And this scalar multiplication that we can see in the slide correspond to the exponentiation. Then we have some hardness in this group. So for instance, discrete logarithm assumption is required to hold, but also other assumptions such as the CDH assumption and this Q power discrete logarithm PDL assumption and many more. Okay, when we want to prove the security of some primitives or assumption in these cryptographic groups, we often require to use strong ideal models to model the group. The most famous one is the GGM, or generic group model, which very roughly speaking is equivalent to suppose the existence of a perfect unstructured group and to give parties access to an oracle that performs group operation for all parties. But this is a very strong and unrealistic model that suffers from some criticism. Particularly, we know that it's impossible to instantiate generic groups. Of course, proof of security in GGM does not prevent attack against group-specific algorithms. And lastly, and this may seem like a technicality, but it's actually a very important point, a reduction in GGM can always program group element with random known exponent. And actually, many proofs in GGM use and rely on these third features of the model. In order to improve and solve some of these criticisms, in 2018, Fuchs-Bowser et al. Introduced another ideal model for groups, the algebraic group model, or AGM. Here, they give adversary access to the real group, but they restrict the adversary to be algebraic in the following way. So the adversary receives input in the form of group element, and then output group element, but the adversary, the algebraic adversary, must provide an explanation of the output in terms of a linear representation of the input. So here the adversary output this group element T in bracket, and it also has to output coefficient alpha, gamma, and beta, such that this linear relation between input and output is satisfied. Okay, AGM solves some of the previous criticisms, so capture some known group-specific algorithm, allow us to do proofs by reduction, but it has some own criticism, and it inherits sums, particularly it inherits the uninstantiability result, at least in the most general form. Now, recent works point out that the relation between GGM and AGM is somewhat shady. And lastly, this is what we focus on this work. We can use AGM as well as AGM to prove the security of knowledge assumptions that are actually insecure in the standard model. This is because algorithm in the standard model can do this operation of sampling group element without knowing their discrete logarithm. Particularly, say that they pick distribution D with super polynomial mean entropy, then they sample a seed from this distribution, and then they use an encoding function to encode the seed into a group element. If we choose the encoding function wisely, then we can show for some encoding, we can actually prove it, that to compute the discrete logarithm of the random variable induced by evaluating the encoding on D is as hard as computing the standard discrete logarithm. So here we can see that even if we give to an adversary the seed, use it to compute this group element X with the encoding, it is hard to compute the discrete logarithm X. And for instance, there exists a family of functions which is called encodings on elliptic curves that has this property. So at least for elliptic curve groups, this is something real. Like real adversary can do these things of sampling a group element without knowing their discrete logarithm. Okay, with this in mind, let me show you this toy example of a knowledge assumption. So we have a challenger that gives the generator to an adversary, and then the adversary sample a group element. We require, by assumption, the existence of an extractor that recover this discrete logarithm X, for instance, because a reduction want to use discrete logarithm. This knowledge assumption trivially holds in AGM and in GGM as well, but due to oblivious sampling, we can see that for what we have seen in the previous slide, that an adversary in the standard model can actually break this knowledge assumption, because if we use these encodings that I've talked before, then under the discrete logarithm, no extractor exists that can compute X. And now you may think that, okay, this is maybe true, but this looks like a very silly knowledge assumption. No one would use it in practice, so why should we care? So let me show you another example. This time, this example is motivated by the Kids AG commitment scheme, which is actually widely used in practice. The challenger now gives a bunch of group elements to the adversary. These group elements are of order sigma evaluated in various power. And then this adversary output a group element, which we can think of this as the evaluation, as the element of order f of sigma. So the evaluation of a given secret polynomial in this trapdoor sigma. And we require, again, the existence of an extractor, and this time the extractor will recover the coefficient of the secret polynomial used by the adversary. This looks like a more reasonable knowledge assumption. So reasonable that it is actually used in the security proof of concrete snarks constructions such as Plonk and Luna. But once again, this is a knowledge assumption that is secure in AGM and GGM, but due to oblivious sampling, insecure in the standard model. So we actually argue that it's important to have an ideal model for group which prevent to prove the security of such spurious knowledge assumption. And this is what we did in this work. So we define AGMOS, AGM with oblivious sampling, in the following way. We give an algebraic adversary more power, allowing it access to a non-programmable oracle. The adversary can query the oracle with pair of function and distribution. Then the oracle will sample a seed from the queried function, from the queried distribution. We'll use the querying function to encode the seed into a group element and then return this pair of seed and group element to the adversary. And the adversary now, when compute its output, has to explain the output as a linear representation, not only in terms of its input, but also in terms of the group element returned by the oracle. So for example, here, if it queried for only one element, then this adversary will also output this fourth coefficient delta, which is the coefficient of the queried element returned by the oracle in these linear relations in the slide. And importantly, the model will not allow the reduction to know the discrete logarithm of this Q element, and will not allow actually any party to know this discrete logarithm. Okay, so how can we use this model? Let me show you how can we prove that the CDH assumption is secure in this new model. We have this AGMOS adversary. We give to this adversary a CDH challenge. Then this adversary can perform its computation. At some point, we'll perform some query to the oracle. The oracle responds as we have described before. And eventually, after many queries and computation, this adversary will output a group element, which is supposed to be the CDH, the output. And then it also provides a linear representation of the output. The adversary wins, of course, if it breaks CDH. So if z is equal to x times y, and since the adversary is algebraic, this linear relations should hold. Starting from these two conditions, which define a successful AGMOS adversary, let's proceed with the proof. So we can implicitly define a verification polynomial using formal variables for the variables x, y, and q involved in the games. So this is the verification polynomial. And in case the adversary is successful, then x, y, and q involved in the game will be a root of this verification polynomial. To go on with the proof, we divide the proof into three cases. Case one says that the verification polynomial is actually 0 as a polynomial, and this we can show that this is impossible. Then case two is the case that this verification polynomial is not 0 as a polynomial, but if we evaluated it in x and y, so it's now only a polynomial in the variable that represent the oracle answer, then this second polynomial is 0 as a polynomial. Intuitively, this corresponds to the case where adversary has not used the oracle group element. And we can show that this happens with negligible probability through a reduction to a discrete logarithm style assumption. And the third case, where also this last verification polynomial is not 0 as a polynomial, we show that these agains happen with negligible probability through a reduction to a new assumption, the TOEFL assumption that we introduced it in this work. So the introduction of the TOEFL assumption is actually the main technical part of this work. Let me just explain you what this assumption is. This assumption is parameterized by a family of function and a family of distribution. And the adversary playing a game where it can interact with the oblivious sampling oracle. And at the end, it has to output a vector. And the adversary wins the game if the vector that it outputs, it's orthogonal to the vector of 1 concatenated to the QIs, which are the discrete logarithm returned by the discrete logarithm of the element returned by the oracle. So basically, these assumptions say that as long as we choose the function of the distribution from these two families, the adversary is not able to use the element returned by the oracle in a meaningful way. Okay, so this is the end of my talks. Thanks for your attention. If you are interested, check the full version of the paper on ePrint, where we have many security proofs to show actually that in most cases things are secure in Agimos. And now I will happily take questions.
Yeah, questions?
Did you manage to find any relationships of your new tougher assumptions with like any standard assumptions?
That's a good question. And actually, I add another slide about the cryptanalysis of Topher. Okay, so the answer is no. And because we decided to have the model that is to have the assumption that is general in order to capture the most general model, which implies sampling from non-uniform distribution and any way that we know to have reduction of this to have a reduction for this kind of assumption implies actually sampling the group element with no the discrete logarithm, or implies to embed a group element that is given as a challenge in some other group elements without alter the distributions. And this is not clear. It's not clear how to do this in the general case. We have a GGM proof for the new assumption to show that it seems that to require that the distribution have super polynomial mean entropy it looks necessary, meaning that if not, there could be some generic attack to this assumption. But also the GGM used for this proof is not standard because we have to assume some sort of hashing. Yeah, I think this is the most important open problems. One good feature that the model has is that the security proof is independent from the specific tougher assumption that people use. So actually, these two are orthogonal problem. We can study security in Agimos of things, and then we can study necessary and sufficient condition on the this function epsilon and d, such that the corresponding tougher holds.
Thank you.
Any other questions? All right, let's thank Roberto and also the other 3 speakers from the session. And we're now off to coffee break.
All right. Welcome everyone to the last session of the conference, and it's a session in composability, consensus, and Byzantine agreement. So for our first talk, we have Michele Ciampi, who is going to talk about agile cryptography, a universally composable approach. Michele, take it away.
Okay, thanks a lot for the introduction. Yeah, this is a joint work with Christian Baderscher and Angelos Kayas. So I'm going to just iterate what Brian Lamacchia have said in a few of his very interesting public talks, which is that basically cryptographic algorithms evolve. Cryptographic algorithms can be broken. You need to change them. You need to update them. That's a very fundamental thing. And this has happened a lot in history. And so that's something we need to take care of. And that's actually something that in practice we do. In practice, we do update softwares. And in particular, we update cryptographic softwares. It's very important to do. And so that's why people have considered in the past the notion of cryptographic agility, right? Which is the ability to reconfigure an application or system with different cryptographic algorithms. And you may want to do that because just you think your protocol may not be secure, or because you want to add some features. I mean, there are many reasons why you want to do that. And the point is that, as I said, this happens a lot in practice, but what we do in theory is that like we have a protocol on the whiteboard, we write the paper, we make the proof, we submit to TCC, and that's perfect. That's gonna be there forever. No need to, to do any change in it. And so it's natural then to ask, like, if we do care about cryptographic agility and updates in practice, why don't we care more even in theory? And that's what I'm trying to cover and to discuss in this talk. And all this discussion will be done in the UC framework, okay? Where what you have is your usual real and ideal world, right? So what happens in the real world is that you have parties running a protocol. They are at version B1, and this protocol realizes a functionality F1, okay? Standard stuff. So now what happens is that for some reason, parties want to update and want to run version 2 of this protocol. So what you would expect is that in the ideal world, this corresponds to parties being registered to a new functionality F2, and that's the update. So you may think that this just corresponds to functionality deregistering from the functionality F1 and register to functionality F2, and everything is fine. But that's not true. That's not what happens. That's not what real an update is, because you don't want to lose maybe something that you did using the previous functionality. So what it means is that there is something which is the state of the functionality F1 that you may want to preserve and keep to the functionality F2. Also, like, who decides when to update and like to what functionality? Like, do we wait for the majority of the parties to say that, or do we wait for a later party to say, okay, let's update now? And also, as I said, we may want to update because things can be broken. But what does it mean that things break in the universal composable framework? So the two contributions of this talk are discussing actually what it means for something to be broken in the real world, in a real world protocol, and then how to capture agility in the UC framework, so that we have the right language, the right tools to talk about this also on a theory side. So when you design a protocol, a real world protocol, what you have is that parties like need to rely on some cryptographic assumptions or on some primitives, for example, encryption, or the fact that the decisional Diffie-Hellman assumption hold, right? So then you use these primitives, you use these assumptions, and you build your amazing protocols, right? They run concurrency, UC allows that, that's fantastic. And what happens is that if some of these primitives are broken, then your protocol may be broken as well. But again, what does it mean that a primitive or that, for example, an encryption scheme is broken? How do you capture that? So the way we capture this in the real world is by considering a special hybrid functionality, which we call fcomp as in fcomputation. And basically, anytime you need to execute an algorithm, for example, an encryption algorithm, what you do is that you initialize this functionality with the algorithm. And when you want to evaluate the algorithm, you query this algorithm through this functionality. And then you can use the output as a protocol message for your complicated MPC protocol or whatever. So you can keep doing that. And at some point, you may have this type of commands which is a subcorrupt command from an adversary, which basically allows the adversary to get the internal state of this fcomp subroutine. So this means that kind of like everything, all the secrets you may have given to this fcomp are leaked to the adversary. And actually from that point on, anytime you wanna query your algorithm, actually your query is forwarded to the adversary, and it's the adversary that decides how to answer this query. Okay, that's how you capture how things are, when things are broken in a real world protocol. And this allows to capture also the fact that assumptions may be broken. So for example, if you need to sample Diffie-Hellman tuples, and most likely you're doing that because you're relying on a Diffie-Hellman assumptions, well, what happens is that you do sample your tuple inside this hybrid functionality, and then when the Diffie-Hellman assumption doesn't hold anymore, what happens is that this corresponds to action and adversary sending a subcorruption command so that the exponents are leaked to the adversary. Okay? So now this is how we model the fact things can break down. Let's say how we model agility. So the way we want to model agility is as follows. So we imagine that there is a set of parties registered to a functionality F1. This functionality has a state. Now what happens is that maybe different parties want to update to different functionality because, I don't know, they feel more comfortable running being registered to F2 instead of F3 or F1, and they like more the interface of this new functionality. So you can have forks. It's this has happened in the past for in computer science, that people didn't like a software implementation, so decided to adopt two different software implementations. And so one of these functionality may be compromised, and you want to heal from it. You want to heal. It means that you want to be registered maybe to another functionality while maintaining actually part of the history, part of the state. That's how we call it here. Okay, and then you may end up in the situation where you merge the parties, the state again, and like now you have this great functionality F5 that has great properties, and everybody like it. So the way we model this is by designing this wrapper that we call, it's a big functionality we call fupdate, which is parameterized by three things. So first of all, there is a class of functionality that this wrapper supports. This is needed because, as I said, you want to preserve the state between updates, and this makes sense only if like the states are, the functionalities have state that are compatible with each other. You have an update predicate that describes when the update is triggered. For example, when the majority of the parties decide to update, or when there is a leader party that decides to do an update. I'll show you an example. And then state update, which says which part of the state you want to preserve. Maybe you don't want to preserve everything. Maybe you are concerned about actually some messages were computed. So you want to preserve only a prefix or a subset of the things you have generated so far using this functionality. Okay. So I'm going to show you an example of how the ideal world looks like when you have this wrapper, and how the real world looks like for the case where you have signatures. Okay. So this is the standard signal functionality. You are all familiar with it, I suppose. So the signature functionality has a designated designated signer. So anytime I want to sign something, the signer says, okay, please sign this message for me. The functionality gives back some special message, a special signature message to the signer. And the functionality records all the messages that are signed. Okay. Now, when a verifier wants to verify, it asks the functionality, whether the message M2 with the signature S2 and the verification PK, whether this tuple is it belongs to this database that the functionality is registering, and if that's the case, then the functionality returns 1, otherwise 0. Okay, that's very easy. So what happens in our framework is that this fupdate will maintain F1, which is a signature functionality, and anytime there is a query related to signing messages or verifying messages, this wrapper forwards acts as a proxy for all these messages, okay, between like the parties and F1, which is again a signature functionality. Now what happens is that fupdate also accepts an update command. Okay? Upon receiving an update command, in this case the signer can decide to update. There is a new functionality that is generated inside this wrapper, and the state is copied to the new functionality, F2. And now if a verifier updates, or like when any verifier updates, and if a verifier that has updated as a query, this query will be forwarded actually to F1 to F2 instead of F1. Okay, that's how you keep track kind of the updates, and that's what you want in terms of state preservation for this very simple example of signatures. Okay? And the point is that you can also have that the functionality is maybe compromised at any point via this subcorrupt command, but the thing is that this should not affect security. Okay, this should not affect the security. What you expect from a signature scheme. So how do you realize that? So here we want to consider the case where an adversary can corrupt a functionality, a signature functionality, even before the update occurs. So as you can imagine, this is not easy to do unless you assume some form of setup. And the form of setup we assume here, it's like the existence of another signature scheme, which we call fcold. I'll talk about this later. So, but the overall idea is that like parties can use this fcold signature scheme, and then at some point the signature scheme may be compromised. But what you can do is that you can heal. You can heal because the signer now wants to update to a new functionality F2 can actually hash all the messages that he has ever generated and sign these messages using this fcold scheme, which is again just a standard signature scheme. And then your update information are made by like this set of messages and the hash, which is signed with this cold signature scheme. Okay? So after that, the signer has updated all the signatures, all the new messages that need to be signed will be signed using this new functionality. And now anytime a verifier needs to verify a signature, the verifier will check whether the signature verifies against the new signature scheme or whether this message belong to this set of messages that are denoted with bold M. Okay? And now you can say, okay, well done. You have realized an updatable signature scheme using another signature scheme. Fantastic. So the point is that this makes sense because you may have the situation where these signature schemes, Fold and Fnew or F1 and F2, like they are very efficient schemes, but for example, they may not be post-quantum secure. Okay? And then you can have Fcold, which is kind of a good scheme, but very slow. It's post-quantum secure, but it has stronger security guarantees. Okay? So the idea is that when you expect things to go fine and you don't want to update, you just use fast schemes. And only the few times that you believe that you need an update or that you believe that there is something wrong going on, you rely on the slower signature scheme that in turn gives you better security and can support you with the update. And this is a very simple example, but you can extend these to other settings, for example, to the zero knowledge setting. And indeed, we have a similar result for this case. And we also consider the case where you want to update implementation of pseudorandom functions while maintaining the same secret key. This is a problem that has been considered in the past in the context of cryptographic agility, and our framework captures this actually. So what is the main takeaway then of this talk? Is that cryptographic protocol need to be updated, and this should be considered when you think about a protocol, when you design it, when you prove it secure with respect to some idealized worth. And yeah, so basically, more or less, that's it. For the other results I mentioned, I would recommend you to look at the paper. And I conclude yeah, by saying that, yeah, if you want to work with me, reach me out. So thank you very much.
Thanks, Michele. We have time for a couple of quick questions. Okay, if there are no questions, let's thank the speaker again. So for our next talk, we have Michael Close, who's going to talk about composable long-term security with rewinding.
thanks for the introduction. So I'm going to talk about our work, composable long-term security with rewinding, which is joined with Robin, Brandon, Jeremias, Jörn, Astrid, and Markus. And so first, I have to clarify what I mean by composable. We're considering a UC type notion, so universal composability, where the security experiment looks like this. So we want to compare a real protocol pi with an ideal functionality F. And in the real world, there is a real adversary A and an environment. And in the ideal world, there's the ideal adversary, the simulator S, and the environment as well, which tries to distinguish this real and ideal situations. And well, computational UC security says these situations are indistinguishable for any polytime adversary and distinguisher. Now, maybe computational security is not enough for us and we want something stronger. For example, we might consider statistical UC security where all the parties are unbounded. Now, unfortunately, in that setting, we need quite strong setups. So maybe we want something in between. So we can look at the setting of long-term UC security, where we have this PPT execution, basically. So adversary and simulator and environment are now PPT, but the distinguisher will still be unbounded. And this allows us to use hardness assumptions during the protocol execution. But after the protocol finished, we have now statistical security guarantees, basically. So even if we use RSA in our protocol and then quantum computers are constructed, everything will be fine if we finish the protocol execution before quantum computers have been constructed. And so this is like relating it to the talk before, a very binary type of agility. We kind of are secure if the protocol completed. And with long-term security, the situation is a bit better with what we can achieve. So for example, we know that we can construct a commitment scheme from only a signature card, or even different assumptions. But unfortunately, there are still quite strong impossibility results. Namely, we cannot construct long-term secure commitments from just a CRS. So CRS hybrid model doesn't help us. And very roughly, the problem here is that if we have just a CRS, well, then if the CRS would not result in statistically hiding commitments, the distinguisher can break them. But if the CRS gives us statistically hiding commitments, then the simulator cannot break them, so it cannot extract them. And we cannot just switch between statistically hiding and not statistically hiding commitments because the distinguisher can distinguish this switch. So what do we do? Well, there's one SK patch. We might not have straight line simulation anymore. We might look at rewinding-based simulation. And this is what we did in this work. So in our work, we define this notion of long-term rewinding UC, where we consider an angel-based notion. I will explain that in a second. This allows us to construct commitments from only a CRS in this long-term rewinding secure sense. We can also construct an OT protocol, which has a kind of one-sided security. So we can statistically protect either sender or receiver. But we prove that it's impossible to achieve full UC security. So we cannot protect statistically both sender and receiver. And to formalize all of this, we introduce a new tool, which we call pseudo-oracles, which are oracles which can rewind. And now let's look at this in some more detail. So what is angel-based UC security? So in angel-based security, there's this global entity, which is called helper or angel, and it will offer special powers to all parties, or it has special powers, and it kind of offers these to usually used only by simulator, environment, and adversary, but in principle also like honest parties could use it. And for example, this power might be that the angel will brute force the committed values of some statistically binding commitment scheme. And it will only do so in judiciously chosen situations, which are made so that the simulator benefits from this, but the adversary doesn't. And we look at a specific angel, or like our construction is based on this prior work from Canetti, Lin, Pass, and Goyal et al., which is a rewinding simulatable angel. So the angel itself is just a straight line angel, which offers us a CCA commitment game. This means we can concurrently run many CCA commitment sessions with this angel. And once we finish such a commitment, the angel will brute force extract the committed value and tell us what we committed to. And as I said before, this angel has the nice property that it is rewinding simulatable. So think of it as this angel having many rounds in which you prove that you actually know what's inside the commitment. And so we can kind of, by using rewinding, simulate this angel without doing brute force extraction, but doing rewinding-based extraction. And now we're in the nice position where we can use the straight line angel doing brute force extraction when we need UC simulation. But when we want to do security reductions to, well, the hardness of D-log or breaking signatures, where it might be a problem to have this super poly power in the game, we can just remove it by using rewinding. Now there is a technical caveat, namely we cannot rewind a security game we're trying to play. So if we just rewind an EUF CMA game, then we might kind of not do a proper signature forgery. So what we have as an extra property is the K-robustness here, which basically says that we can exclude K messages from ever being rewound. So we can have what is called a left side here. On this picture, it's B, and B will never be rewound by this rewinding simulation R. And this is what we base our construction on. We also use a CCA commitment oracle, constructed somewhat differently, because we need rewinding-based simulation and not just rewinding simulatable angels. And for that, we need to define what it means that an oracle or an angel can rewind. And let me first say what an oracle does. So an oracle basically is just an ITM. It's a stateful machine. You can send a message to it. It will respond with an oracle response. And this makes it inherently unable to rewind anything. So we define this notion of pseudo-oracle, which when you send it a message, it actually gets the state of the caller, like not the state, the view of the caller. And thus it can rewind the caller in its head and do rewinding things. And well, one thing is that this behaves very differently from usual oracles. So the properties are different. So as a first thing, we just want to deal with these pseudo oracles when they are actually black box. So they should not really use the view of A because that's harder to deal with. They should just use A as a black box. Now, as a second property, we want that we basically have the rewinding-based, the rewinding simulatability from these prior works. So as long as we have some K-round left side, we want to be able to replace the oracle with a rewinding-based simulation so that the outputs are statistically close. And finally, we want a notion which we call K-robust composition order invariance. And that is a crucial notion, which I'll explain on the next slide. So with oracles, all of this is trivial. And what all of this is about is what happens if we compose two systems in different ways. So on the left side, you see that we first connect A with this pseudo-oracle, and then we connect this composed system with B. And on the right side, we first connect B and A, and then we plug in the pseudo-oracle. Now, what does this mean for pseudo-oracles? It means that on the left side, the pseudo-oracle gets the view of A, or it gets black box access to A, but it's unable to rewind B. On the right side, it's able to rewind this machine B composed with A. So this is inherently very different. And what composition order invariance guarantees for pseudo-oracles is that nevertheless, the outputs are statistically indistinguishable. And with this, I can address some maybe major question about all of this. What is the meaning if we have like a rewinding-based helper? So we have this ideal functionality, say it's OT, and now we rewind the ideal functionality, and somehow we actually see then both OT messages maybe. So what does this mean? And this is where we crucially rely on this composition order invariance, because it allows us to exclude the ideal functionality from the rewinding altogether. And now it's meaningful that there is this ideal functionality because it's never rewound. And of course, we need the K robustness. This works for K round ideal functionalities, and K can be chosen arbitrarily large, but that also means that this commitment scheme will need an arbitrarily large number of rounds. And with that, let me conclude. So we define this notion of long-term rewinding UC, which somehow brings a rewinding-based simulation to UC. And we give some possibility results. Unfortunately, we also have strong impossibilities. And we define this notion of pseudo-oracles to handle this rewinding in oracles. Thank you.
Thanks, Michael. Do we have questions?
Hi, thanks for the talk. So I was wondering, what's the running time of these extractors like? I mean, I expect that they are expected polynomial time, right? Not strict. So how does it play a role? It should play a role in the reductions, right?
Does not properly explain the rewinding, but we rely on the PRS Bakaran-Rosen-Zahai, I believe, rewinding schedule. We have a super logarithmic number of rounds, so that we actually get a polynomial like PPT rewinding. I think it's quadratic overhead, but everything is PPT. This is why we don't use the Canetti-Lin pass approach, but base our approach on Goyaleka.
Right. So this approach inherently needs many rounds, let's say, to yeah. Okay, makes sense. Thank you. Thank you.
We have time for one more questions. Well, if not, let's thank the speaker again. Okay, for our next talk, we have Benjamin Chan, and he's going to talk about simplex consensus, a fast and simple consensus protocol. Benjamin?
Awesome, thank you. Can you hear me, everyone? Okay, so I'm pleased to now switch gears from UC and composability to Byzantine agreement and consensus, which is, I think, my favorite primitive. It's really pretty, it's really fun to work with. Hope you enjoy it too. Okay, so this talk, we're going to show you a consensus protocol with the easiest security proofs, which is subjective, of course, and the best latency of all the protocols we've seen thus far. And it's going to be for the partially synchronous f less than n/3 PKI setting. I'll go over that later. And why is this important? Well, consensus is a key primitive for blockchains, and in particular proof of stake blockchains in this setting, and also for MPC and broadcast. And why do we care about easy security proofs? Well, I think this area has been very well studied. These consensus protocols date back to the 1980s, 1970s. But to this day, in my opinion, our opinion, these protocols, prior work, have largely non-trivial liveness proofs and are relatively hard to intuit still. So we're always looking for a nicer, easier protocol to study and to teach. And our goal is indeed a practical protocol that is intuitive enough to just teach in class. And my goal is maybe when you walk away and you think, hey, how does consensus work? I hope you think about this protocol. I think the high ask, but we'll try. And I'll try to teach the whole protocol today, including the security proofs in 10 minutes. So we'll see how it goes. Okay, so the setting is the following. We have n players, f of whom are malicious. F is less than n over 3. They're Byzantine faults, static faults for now. And we are in this partial synchronous network, which I'll define soon. We know everyone's public keys ahead of time, so we assume a bare PKI. And generally, what's going to happen is this. This is the problem. Players are going to receive transactions from this environment over time. Different players may see different orders of transactions. And players will have to continuously output a log of so-called finalized transactions. And we require two properties here. The first is consistency. All players must output the same ordering of finalized transactions. This is our agreement property. And next, we need liveness, which is that these transactions do eventually get output and finalized by the protocol. Okay. Partial synchronous here is a specific model that dates back to 1988 that models an unreliable network setting. So basically, the network can be divided into a period of bad network time and good network delivery. So there exists some unknown time GST such that after GST, every message in the network is delivered within bounded time. And we know an upper bound for this delivery bound. And before GST, there is no guarantee on message delivery. So messages may be delivered out of order, they may be dropped. And here's our theorem statement. Assuming a bare PKI and collision-resistant hash functions, there exists a partially synchronous random leader consensus protocol for f is less than n over 3, static corruptions, and a bunch of latency metrics, which I don't have time to talk about today, and really easy security proofs. And that's going to be the focus of my talk, really understanding how this protocol works. I will note that we get efficient communication via the techniques of Algorand, so we won't really worry about that. And I think it is worth sort of looking at, hey, there has been a lot of work for protocols exactly in this setting. A lot of them have been deployed on the internet. And I will say that our protocol seems to, at least theoretically, be a little faster in various notions, which I won't have time to go through. A fun quick note before I dive into the actual protocol. All these protocols differ only slightly in the protocol description. I think consensus is this kind of fun area where you tweak the protocol a little bit and all of a sudden everything changes. And so our protocol hopefully will give some intuition on why all of these other prior works also work. Okay, are we ready? Protocol description. Okay, so let me set up a bunch of data structures and preliminaries. The first key data structure is blockchain, which I didn't expect to hear at TCC. So each block of height h is just going to be a tuple of the form h, comma, a hash of a whole parent chain. So you're really committing to a whole parent chain, and a set of transactions. Okay, and here, for the purposes of this talk, we're going to hash all the previous blocks, and so on and so forth. We also allow the blockchain to contain these, quote, dummy blocks. This is new to our protocol. A dummy block of height h is just the tuple h, comma, bot, comma, bot. Okay? It's an empty block. It doesn't have a parent. And again, every block that's not a dummy block has to extend a parent chain. So once again, voting for blocks. So a player I, quote, votes for a block by just signing the message, I vote for that block B. Okay, and we call a notarized block, well, rather, a block is notarized in my view by seeing more than 2n over 3 votes for that block, or rather signatures from more than 2n over 3 players. Dummy blocks can also be notarized. So if we see signatures from more than 2n over 3 people for the dummy block. Okay, and a notarized blockchain is just a blockchain where every single block in the chain is also notarized, except for the genesis. And so you might be asking, why 2n over 3? What's so special about this number? The neat little lemma that we'll use throughout the talk, and it's a very famous sort of, I mean, everyone uses it. It's called quorum intersection. And the property is if honest players only vote for one of B or B prime, then it cannot be that both 2n over 3 players vote for B and 2n over 3 players vote for B prime. right? Why is this true? Well, corrupt players can always vote for both of the blocks, but honest players here only vote for one of them. So there's n minus f votes on the left side, 2 f votes on the right side. If you sum them up, there's less than 4n over 3 total, since our fault tolerance is set less than over 3. So form intersection should hold. Okay, we're ready for the protocol, the simplex consensus protocol. We proceed in iterations h equals 1, 2, 3, so on and so forth. And in each iteration h, we'll collectively try to build a notarized block of height h. Okay, so in iteration 1, we want to see a notarized block of height 1, and so on and so forth. And we move to the next iteration only when I've seen a notarized blockchain of length h. And when we do move, we do send this notarized blockchain to everyone else, just for simplicity. Okay, so how do we actually construct a notarized block within each iteration? Well, first, each iteration will have a leader player chosen randomly ahead of time. Here, we'll just let the leader of iteration h be a hash of the current iteration number, mod n. And we model it via a random oracle, but you can use it use another hash function. Okay, and now we're ready. So each player on entering iteration h, if they're the leader, okay, they're going to choose a notarized blockchain of length h minus 1 and extend it using a new block, b sub h. And then we're going to send everyone a signed message. Hey, I propose this new block. This new block should contain all pending transactions. And everyone else, or all the voters, on seeing the first valid proposal from the leader, is going to sign a message, I vote for this block. Okay? And importantly, they only do this once. They only do it for the first valid proposal. And of course, if the network is good, and we're after GST, and the leader is honest, then this block proposal will get notarized eventually, soon. And just to preview, we know that at most one block proposal from the leader will ever be notarized in honest view because of a simple application of quorum intersection. Okay, so that seems really nice so far. But how do we handle faults? Right? The whole shebang is handling faults in distributed computation. So like maybe the network drops all the messages, or the leader crashed, or maybe we just never saw a block proposal. What do we do in iteration 3 here? Or maybe a faulty leader sent different people different block proposals, so honest players split their votes, and no one got 2n over 3 votes. So no block gets notarized. So what do we do? How do we move on? And our solution is dummy blocks. So if 3 message delays worth of time have passed since a player has entered iteration h, then that player, and that player has not entered the next iteration, then that player will sign a message, hey, I vote for the dummy block of height h. Okay? And I'll vote for the dummy block, and eventually, well, if no one makes progress, everyone's going to sign the dummy block. And everyone should see a notarized dummy block in their view, and then subsequently move on to the next iteration. That's quite nice. Now, a quick interlude. Just for intuition, you might realize that due to faults, we might see both a notarized block proposal for height h and a notarized dummy block for height h in the view of honest players. Like for instance, maybe Alice saw the leader propose a block and people sign that block and enough signatures. So I see a notarized block proposal for h equals 3. But maybe, everyone else timed out due to asynchrony. The messages got dropped and voted for the bottom, the dummy block. So maybe Bob sees a notarized dummy block of height 3. Note that both of these are valid blocks to extend for the next leader. And I think for an agreement, we really do need to decide on a single block at each height h. And this is sort of the agreement property. We want to choose a blockchain. Okay, so this is the final piece of the protocol. When player I enters iteration h plus 1, if I did not time out and vote for the dummy block for h, then player I will send everyone a signed, quote, finalize h message. And on seeing 2n over 3 finalized messages for h, a player I finalizes any notarized blockchain of that height and the transactions inside, and now these are final, and we have agreement on the contents of this blockchain. And brief intuition, if I do see 2n over 3 finalized messages for h, then no honest player should ever see 2n over 3 dummy votes. So the dummy block of height h cannot be notarized in honest view. and that's nice. Let me now prove this protocol secure. So first, let's argue consistency. So suppose Alice and Bob are two honest players, and Alice outputs some log, and Bob outputs another chain called log prime. Then I claim that Bob's chain extends Alice's chain. Okay, so consider Alice's chain, which is, sorry, without loss of generality, the shorter one. Let its length be h. I claim that there can only be one notarized blockchain of length h across all honest views. Okay, and therefore Bob's chain must extend Alice's chain. So the first claim is that at most one block proposal from the leader of H can be notarized in honest view. And this is just because each honest player votes for at most one honest proposal or one proposal, and you apply quorum intersection. And the second claim is that since Alice finalized this chain, she must have seen 2n/3 finalized messages for H. And therefore, the dummy block of height H cannot be notarized in any honest view. And again, this is by quorum intersection, because each honest player will either vote finalize or for the dummy block. So that's easy. Bob's chain, by virtue of being notarized, must now extend Alice's chain, and we've just shown you agreement. And here's the liveness proof. This is the one that everyone, well, I think most people don't write one down, or they're rather relatively vague. So here's the liveness proof. So if the network is good and we're after GST, then I claim that an honest leader can always get its block proposal notarized and then finalized. Okay? And the fact that we're going to rely on is that if some honest player enters iteration h by time t, and t is greater than GST, then every honest player will enter iteration h soon thereafter, after one message delay, by time t plus little delta. Little delta is the message delay here. And this is just because when an honest player enters an iteration, will send its notarized blockchain of length h minus 1 to everyone else. Okay, so here's the proof. Let t be when the leader of iteration h enters iteration h, and when it proposes a new block. Subclaim 1. Every honest node will see a notarization for some block of height h by time t plus 2 little delta. Okay, so we know that by time t plus little delta, every honest player enters iteration h and sees the proposal. So they'll either vote for the block, or one of them must have already entered the next iteration. So therefore, by one more message delay later, every honest player should see some notarized block of height h. Subclaim 2, the dummy block of height h cannot be notarized in any honest view before this time t plus 2 little delta. Why is this true? Well, the earliest any honest player can enter iteration h is at time t minus delta. And the earliest any honest timer can fire is 3 big delta after that. So you can sort of see, hey, the timer's just not going to fire by time t plus 2 little delta. So whatever block got notarized has to be a valid, like a real block. So they all send a finalized message, and everyone should finalize their chains. All right, the final little claim of this talk is liveness for faulty leaders. So if the network is good, any iteration, even with a faulty leader, should conclude after 3 big delta plus little delta time. And this is just because, well, if enough time has elapsed, either everyone will fire their timers and vote for the dummy block, or some honest processes already enter the next iteration, in which case, everyone will enter the next iteration soon thereafter. Okay, so that's simplex consensus in a nutshell. I thank you, and hopefully it's interesting.
Thanks, Benjamin. We have time for one super quick question. So maybe I'll ask one. Do you have a sense for how the protocol behaves in the fully asynchronous settings?
Protocol isn't exactly well defined in the fully asynchronous setting because so when we vote for the dummy block, we time out. We have to wait some preordained amount of time in which we have to allow the honest guys to try to do some work. In the asynchronous setting, we have no such upper bound on how long we have to wait. So yeah, asynchronous protocols are also very interesting and I think an active area of research.
Thank you. So let's thank the speaker again. Oh, okay, so our next talk will be online. And I was told that you can still ask questions because the speaker will be online. But yeah, without further ado, so let me welcome Rutvik Patel, who's going to talk about concurrent asynchronous Byzantine agreement in expected constant rounds revisited. And we'll play the video.
I think it's on the bottom right of the player.
We also investigate round preserving. My name is Rutvik Patel, and I'm going to talk about our work revisiting the problem of obtaining concurrent asynchronous Byzantine agreement in expected content rounds. This is joint work with Ron Cohen, Puyan Fergani, Juan Garay, and Basil Sikas. Let me start by introducing the problem of Byzantine agreement, or BA for short. Here we have n parties connected by a complete network of point-to-point channels. Up to t of the parties may be corrupted by an adversary, who we assume is fully malicious or Byzantine. Each party PI has an input value VI, and we require two properties hold. Agreement, meaning that all honest parties output the same value, and validity, meaning that if all honest parties start with the same value V, then that must be their common output. It's well known that without a trusted setup, like a PKI, BA is possible only if less than a third of the parties are corrupt, T less than n over 3. And this holds even if you allow cryptography or randomization. While this problem originally comes from distributed computing, BA, as well as its closely related single-center variant broadcast, are important building blocks in the construction of cryptographic protocols. We consider BA in an asynchronous network. In this model, there's no global notion of time within the protocol, and messages sent over a channel are only guaranteed to be delivered eventually. In particular, the adversary can delay messages for an arbitrary yet finite amount of time. The main challenge in this setting is that you can't distinguish between a silent corrupted party who's not sending messages and a slow honest party whose messages are simply delayed. As a result, an honest party can't wait to receive messages from more than n-t parties at any given stage of the protocol. The FLP possibility result states that no deterministic asynchronous BA or ABA protocol can tolerate the death of even a single party. Thus, randomization is necessary to achieve ABA. One primitive commonly used to provide this randomization is the oblivious common coin, or OCC, which guarantees that with constant probability, all honest parties output the same random value, V and D. The coin is oblivious because the parties don't know whether agreement has been reached. This domain D need not be binary. In fact, its size can depend on n, but even a binary OCC is quite powerful. Rabin showed that ABA reduces to a binary OCC. The resiliency of his construction is quite poor, T less than n over 10, but he actually achieves expected constant round complexity. Feldman, in an unpublished manuscript, showed how to actually implement this binary OCC from secret channels in constant rounds for T less than n over 4. He also gave a better reduction, achieving expected constant round ABA for T less than n over 3, which is optimal from a binary OCC. Finally, Canadian Rabin completed the picture by constructing a binary OCC for T less than n over 3. Let me just give you some idea of how we can achieve ABA from a binary OCC. The high-level idea is to proceed in rounds, starting with the original input values. And in case of disagreement, the parties adopt the value of the coin for the next iteration. Actually, a multi-valued OCC is also generally useful for consensus tasks. For example, it enables oblivious leader election, or OLE. Just being able to elect a random leader with constant probability can provide the parties with sufficient coordination. To our surprise, asynchronous OLE doesn't seem to exist. A number of works by Benner and Eve, Fitzy and Karai, and others point to the paper of Kennedy and Rabin or Feldman's manuscript for instantiating this primitive. But a closer look reveals that these constructions provide a binary OCC only. And it's not immediately clear how to extend to larger non-constant sized domains. For example, the obvious approach of running log-n executions in parallel only yields agreement with inverse polynomial probability. Clearly, this is a major hole in the literature that has gone unnoticed for decades. More specifically, no existing OCC protocol is simultaneously optimally resilient, asynchronous, multi-valued, and information theoretic. We provide the first construction satisfying all four requirements. We also investigate round-preserving parallel composition of ABA. This turns out to be non-trivial, and to see why, we need to take a detour to so-called probabilistic termination protocols, by which I mean protocols for which there's no fixed upper bound on a party's termination round. This includes expected constant round ABA. As a simple example, consider flipping a coin. How many flips are expected until the coin comes from heads? The answer is obviously 2, and fixing the bicep of the coin, in general, a constant number of flips are expected. Now what if we flip n coins in parallel? How many flips are expected until they all come up heads? Here the answer is log n, and viewing these flips as deciding on whether to terminate in a round or iteration, the conclusion is that running probabilistic termination protocols concurrently doesn't preserve expected round complexity. The motivation is that we often compose multiple BA instances in MPZ protocols, and we would like to do so without blowing up the round complexity. Benner and Eve pointed out this issue, and they actually solved concurrent BA, synchronous BA, as well as concurrent ABA, still in expected constant rounds for t less than n over 3. Upon investigating their asynchronous protocol, however, we discovered a number of issues. First, let me give a brief. Let me briefly review their construction. The idea is to run a batch of executions per ABA instance for a small constant number of rounds, and setting parameters appropriately. This guarantees that with constant probability, at least one execution per instance will have terminated. Parties can then select a representative output for each instance. However, the parties might not terminate in the same round for each instance. So they need to distribute these vectors of candidate outputs and then elect a leader to coordinate. The same general idea underlies their synchronous construction, but due to message dispersion issues in asynchrony, their concurrent ABA protocol is very complicated, and there are some issues in the proof. It also suffers from missing building blocks. Asynchronous OLE, which we can instantiate using our multi-valued OCC, but also multi-valued ABA in expected constant rounds. And for the same reasons I discussed on the last slide, this doesn't follow directly from binary ABA in expected constant rounds. We address all of these issues by designing a new protocol, which is simple and modular. Before I get into the technical content, let me end with this bird's eye view of the asynchronous landscape for t less than n over 3. So we would like to obtain expected constant round asynchronous MPC from point-to-point channels, for which we have the recent construction of Cohen. This relies on expected constant round concurrent ABA. The protocol of Benner and Eve relies on expected constant round multi-valued ABA, which we can instantiate using the OCC-based binary ABA protocol of Kennedy and Rabin, along with the reduction, the extension from binary to multi-valued ABA of Mostafa and Renault. But Benner and Eve's protocol also relies on constant round asynchronous OLE. And as you can see, that box is just hanging. So in this work, we fill in that gap, and we also propose a new expected constant round concurrent ABA protocol. Let me now give you some, let me now go over our multi-valued OCC construction in some detail. As a starting point, we take the binary OCC of Feldman and Canadian-Rabin. Recall that Feldman achieved resiliency T less than n/4, and Canadian-Rabin optimal resiliency T less than n/3. But the OCC protocols are essentially the same once you instantiate, once you realize asynchronous VSS. At a high level, the protocol proceeds as follows. Each party starts by secret sharing n random field elements, one per party. Then after some rounds of message exchange and reconstruction, a vector of n random field elements becomes fixed. And n minus t elements of this vector are visible to each party pi. N minus t due to asynchrony. However, it is guaranteed that there's an intersection of size at least n/3 among the local views of all honest parties. Feldman and Canadian-Rabin extracted a single bit from this. We were able to do much better via a combinatorial lemma, which we believe might be useful in other contexts as well. Consider a vector of length n consisting of random values from some set S, and let I be any constant fraction of indices in this vector. If the size of S is theta of n squared, then with constant probability there will be at least one repeat in V, but all repeats will lie inside I. And the intuition for this is that when S has size O of n squared, there's at least one repeat in any constant fraction of V with constant probability. This is essentially due to the birthday paradox. And on the other hand, when S has size omega of n squared, there will be no repeats in V at all with constant probability. There's a sweet spot between these extremes that can be leveraged to extract shared randomness. To apply the lemma, we take that vector of random field elements at the end of the OCC protocol. When t is less than n/3, we have a common subset of indices, common subset of n/3 indices known to all honest parties. Then if we work over a field of size n squared and have parties output the repeat with minimum index or maximum index, doesn't really matter, in their local view, we get an n squared valued asynchronous OCC. This can be easily generalized to arbitrary domains, even exponential size domains. And as a special case, when the size of the domain is n, we get asynchronous Lewis leader election. Lastly, let me give you some idea of how how our simplified concurrent ABA protocol works, as well as discuss the issues in Ben-Ornell-Neve's concurrent ABA protocol. I said earlier that there's low dispersion in asynchronous networks. Let me elaborate on that first. Suppose we have 3 t+1 parties, which distribute their messages using a reliable broadcast protocol. If we look at the messages received by 2 parties, P1 and P2, the adversary can manipulate delays so that the size of the overlap is only t+1. When we add a third party to the mix, this decreases to 1. And with just 4 parties, the intersection of their views can be empty. However, all honest parties will eventually receive each other's messages. So n-t parties should have an overlap of size n-t. Ben-Ornell-Neve achieved this with a sequence of primitives: acast, acast plus, spread, select. Never mind what those are, but the point is that this is a layered structure with non-black box calls to lower level primitives. And this makes their concurrent ABA protocol error-prone and difficult to analyze. And in fact, there are some issues with part of their analysis. In the paper, we actually give an attack. We also show that the idea that all this complexity comes with a territory is really a myth. Indeed, our solution is much simpler. Following Ben-Ornell-Neve, we start by running a batch of truncated executions for each ABA instance. Then we run ABA on continuation. If the parties decide to continue, then they're able to distribute a representative output for each instance. Now here we add several rounds of message exchange and show, using a counting argument, that messages from at least n/3 parties are received by all honest parties. Then we use our asynchronous oblivious leader election protocol to elect a leader. And finally, we run multi-valued ABA on the leader's output vector. And this doubles as agreement on termination. This is not quite enough, however, as we need to validate the output. So, for this, we make use of some additional properties of ABA, which are nevertheless easy to obtain, along with some validation that occurs in the distribution stage. And in this way, we obtain expected content around concurrent ABA. As you can see from this side-by-side comparison with Benor and Elneve's concurrent synchronous VA protocol, our protocol is remarkably simple. And this is pretty much the ideal. This is pretty much ideal when designing an asynchronous counterpart to a synchronous protocol. In summary, we construct the first optimally resilient asynchronous multi-valued and information theoretic OCC. This feasibility result is novel and yet has been assumed in the literature. We also construct the first simple and sound expected content around concurrent ABA protocol for the optimal TLS number 3. And we also give a composable treatment in UC. This presents some interesting modeling, some interesting challenges in the modeling in the simulation, which we deal with. Thank you, and please see the full version on ePrint. My name is Rutvik Patel, and I'm going to talk about our work revisiting the problem of obtaining concurrent asynchronous Byzantine agreement.
Thank you. So we're running a little bit late on schedule, but maybe we have time for one super quick question for Rutvik, who should be online. Meantime, the next speaker can start getting ready. Okay, if not, let's thank the speaker again. Okay, so for our next and in fact last talk of the conference, we have Gilad Stern, who's going to talk about zombies and ghosts, optimal Byzantine agreement in the presence of omission faults. Please.
Thank you. Thank you, I'm Gilad. I'll be talking about mixed fault tolerance. This work is a joint work with Yulin Lofts. So a little bit of background in our model. We're going to work in a synchronous network of n parties. And by synchronous here, I just mean the regular round-based models. And we have n parties that have point-to-point channels and can just talk to each other. In this network, in this type of network or in this type of kind of task, we often have all kinds of different fault types. So for example, we sometimes deal with Byzantine faults. Byzantine are just fully malicious parties that can deviate from the protocol and kind of hurt it actively. We have receive faulty parties that might have messages sent to them dropped. We have send faulty parties that are the opposite. Messages that they send can be dropped. And finally, we have crash parties, just stop participating in the protocol fully. These are some of the most common types of faults. Now, throughout this talk, T, R, S, and C are going to be the numbers of Byzantine, receive, send, and crash faulty parties, respectively. Now, ideally, I would like to always kind of have Byzantine fault tolerance. In some sense, it's the most tolerant. I can think of other faults as kind of special cases of Byzantine faults. Now, there's an issue that Byzantine faults are a little limiting. So, for example, we know how to do Byzantine consensus with n greater than 3t. We know we can't do any better. But if we just deal with omission faults, for example, with receive faults, we can deal with any number of receive faults if we want. So we can kind of deal with more benign faults, unsurprisingly. Now, in addition to that being limiting, it might not always be realistic to have really large attacks, really large Byzantine faults. So in some networks, I can say maybe I'll have a small number of parties actively attack me, but the network might still be highly unreliable, and some parties might not receive messages or might have messages dropped. So it's not only limiting, it might not be necessary all the time. We kind of want to talk about how to deal with both types of faults at the same time. All right, so we're not the first ones to think about this task. There's been a lot of work about this. There's been some work in the 90s. There's been a little bit of work in the 2000s. And we know how to do all kinds of stuff. So for example, we know how to do unauthenticated consensus with n greater than 3t plus c in the crash case, and n greater than 3t plus r plus s in the omission case. Now, there are all kinds of works that do this. These are just three of the most resilience work we know about. Now, recently, both Julian and I worked on kind of doing some more, kind of extending this line of research. The first of these two works deals with authenticated consensus with n greater than 2t plus c. And here by authenticated and unauthenticated, I just mean without having signatures or with having signatures. And the second of these works achieves resilience of n greater than 2t plus r plus s in the omission case. Now, note on the second work, two notes. First, they also have a lower bound that shows that you can't do any better than 2t plus r plus s. It's not possible. Now, unfortunately, they don't quite solve the problem as stated. In order to get this resilience, they assume spotty faults. And spotty faults are kind of this extra assumption of faults in which we state that the adversary has to choose in each round either to drop all of the messages for a given party or none of them. It can't drop, let's say, 3 of them and make the others go through. So it should be noted that they also have another protocol that doesn't assume this spotty failure, but it's less resilient. In this work, we close this gap and show an authenticated consensus protocol for n greater than 2t plus r plus s without any assumption on kind of the fault structure. All right, so I'm going to talk a little bit about how we do this. I'm not going to talk a lot about how we do this because consensus protocols can be a little scary stacks of protocols. I'm going to talk about kind of the major ideas in our solutions. Zikas, Hauser, and Maurel, in one of the papers I cited in the previous slide, show how to solve this type of task by using self-detection. They noted that the omission parties won't actively deviate from the protocol, at least intentionally, but they might act on partial information if they don't receive messages. And that's often just as dangerous. So they rely on these parties, specifically on receive faulty parties, to detect their own failures and then stop participating if they see that they're going to hurt the protocol. And they call this zombification. They become zombies and stop participating. They do this, they start by solving just point-to-point sending, regular message sending in a detectable way. And then they kind of construct a consensus protocol on top of that. So how does this work kind of conceptually? Here we have a network. We have the smiley faces are non-faulty parties. The monkeys with hands on their ears are receive faulty. They might not hear stuff. The monkeys with hands on their mouths are send faulty. They might not send stuff. And we want to solve the very simple task of sending a single message. That's it. We want to do this in a detectable way. So if we just send the message normally, we don't add any more information, and this message is dropped, the receiving party just doesn't really know what happened, right? It could be the case the sender is Byzantine and decided not to send a message, or send faulty and the message could have dropped. Or maybe the receiver is receive faulty and it should detect its own fault, right? And if it doesn't do that, then we failed in our task. So they propose to not send messages directly, but to send them through the whole network. When you send the message through the whole network, some of the messages still might be dropped, right? So for example, the top left monkey is receive faulty, it might not hear the message. And then every party forwards what they heard to the recipient. And it should be noted that parties always forward stuff, even always say what they heard, even if they heard nothing, right? So the top left monkey is forwarding the bottom message. I didn't hear anything. Now, some of these messages can also be dropped. And now the recipient just counts. It checks how many messages it received. If it received a large number of messages, we need to actually do the counting, but we can argue that it received the correct message from the sender as well, and it can just continue the protocol normally. and act as if it received it normally, as if it received it directly, I mean. Now, on the other hand, if a lot of the messages are dropped, it can know that it is actually received faulty, right? It knows that it cannot be the case that it heard very few messages if it is not faulty itself. And then it can detect itself and become a zombie and stop participating. Act as if it received nothing and stop from this point on. So in our work, we detect this idea to also include send faults. And we have send faulty parties also detect their faults, stop participating by becoming ghosts, in addition to receive faulty parties becoming zombies. We define undead versions of protocols that kind of include this idea of detection. And we want the detection to have two properties. So first, we want only correct detections in some sense. We want that only receive faulty parties will become zombies, and only send faulty parties will become ghosts. We don't want parties to detect themselves unless they're actually faulty. Now, a second thing here is we want parties to detect themselves if they don't act correctly. We definitely want that to happen. So if a party is not a zombie or a ghost, that means it actually sent or received the messages correctly, and that's the only reason it didn't become a ghost or a zombie. And we start with another primitive weak multicast. So here we have another network. We have a sender on the left. Maybe you're right, sorry. Stage left, stage right. On the far end, it is send faulty. And it wants to do the kind of very simple task of just sending a message to everybody. That's the task of multicast. Sending the message to party 1, then to party 2, then to party 3, etc. Now we want to do this in a way that it can detect its own fault. And here we want it to detect itself unless at least one honest non-faulty party heard the message. If at least one non-faulty party heard the message, it can continue acting normally. And if that is not the case, then it should become a ghost. That is, as a side note, that is enough because if at least one non-faulty party heard the message, it will be able to forward it in the next round. Everybody will hear it in the next round. So it's a very kind of weak requirement, but it's strong enough for us. So here, we want to send the message to everybody. And again, like before, if we don't do something to kind of detect our own faults, the message could be dropped everywhere. And the sender just won't know that it was dropped, right? Unless people say something. So this is not enough. We can't just multicast normally. What can we do? We can have the sender send the message. Note that some of these messages may be dropped, right? For example, the top two parties are receive faulty, so they might not receive the message. And then afterwards, parties will reply with the messages they received, or bottom if they didn't hear anything. And now we kind of do the same trick. We just count. If the sender receives a small number of bottom values, it knows that at least one non-faulty party heard the message, and we're fine. In the next rounds, things will work out. Just continue the protocol as normal. Now, on the other hand, since the sender is actually send faulty in this picture, a lot of the messages can drop. And if a lot of the messages drop, then it will receive a lot of bottom values as replies, right? If it receives a very large number of bottom values, it knows that it actually must be faulty, right? It cannot be the case that nobody heard from it, but it's not faulty, or very few people heard from it. If that is the case, it can become a ghost and stop participating in the protocol in order not to hurt the rest of the protocol. All right, so these are kind of the basic ideas in our protocol. It should be noted that I'm actually slightly lying. Parties actually also do zombification in the other protocol, but kind of the new idea is this, also noticing send faults. In conclusion, we wanted to bring up mixed faults as a reasonable model. We think it's reasonable. We think it's often very realistic and kind of easier to deal with. We formulate undead versions of consensus and related protocols. We construct an authenticated undead consensus protocol for n greater than 2t plus r plus s, which matches the lower bound. And like other works, we rely on self-detection and extend the idea of zombification to ghosts as well. Thank you very much.
Thank you very much. Questions? not. Let's thank the speaker again, as well as all the speakers of the conference. And but before you go, I think there's some announcement from
there's
from
closing remarks from the local chairs. But first, let's thank the speakers of the session and the conference.
Okay. So we have some closing remarks. Could Alon Rosen join us? So this is TCC. I mean, at many other conferences, the general chairs stands with organizers of the next conference and say goodbye and welcome. So we ask Alon to come here. And so I hope that everybody has enjoyed. Please clear everything and be out of here by 5 o'clock, which is also when the bus will leave for Nangang Station. And remember to take all your belongings because this place will soon be closed. And wireless will go dark very soon after we close. Yeah, I think that's it. 那个他的那个投影片，就是那个介绍那个的投影片，就是介绍意大利的，你没拿到 ？OK， sorry, there's a screw up. They didn't get to the. It's okay, we don't need the slide. Yeah, okay.
So let's thank again the amazing organization. That's a great opportunity to do so. And next year it's our turn in Milan, beginning of December. I remind you, submit your best work. That's the most important thing. All the rest is secondary. And I hope to see you again.
Okay, so the conference is adjourned.
And final word from the program chairs. Thank you very much. Thanks everyone for coming, and we hope you had a great TCC.